Welcome to the Sleepless Universe. In this video, we'll take a slow journey through some of the strangest and most fascinating places in the universe, perfect to fall asleep to. Don't forget to like and subscribe if you enjoy this kind of content. And feel free to let me know in the comments where you're watching from and what time it is for you. And now, I wish you a good night and enjoy listening. The Boötes Void. Imagine floating through the cosmos and suddenly finding yourself in a place so vast and empty that it defies comprehension. Welcome to the Boötes Void, one of the most profound absences in our universe. This cosmic desert stretches across 330 million light-years of nearly empty space, earning it the nickname, the Great Nothing. To understand the sheer magnitude of this emptiness, consider that our entire local group of galaxies, including the Milky Way and Andromeda, could fit inside this void more than 1,000 times over. The Boötes Void is so large that light itself, traveling at its constant speed of 186,000 miles per second, would take over 300 million years to cross from one side to the other. What makes this region truly extraordinary is not just its size, but its emptiness. In a typical region of space this vast, astronomers would expect to find approximately 2,000 galaxies. Yet within the Boötes Void, only about 60 galaxies have been discovered, scattered like lonely islands in an ocean of darkness. These few galactic inhabitants are arranged in a peculiar tube-like structure that runs through the void's center, as if the universe had punched a cosmic tunnel through space itself. The discovery of this cosmic vacancy happened somewhat by accident in 1981. Astronomer Robert Kirshner and his colleagues were conducting a routine survey of galaxy redshifts when they noticed something peculiar in the constellation Boötes, where their instruments should have detected the familiar glow of distant galaxies. They found instead an unsettling absence. It was as if someone had carved out a spherical chunk of the universe and left behind only the faintest traces of matter. Scientists initially struggled to explain how such an enormous empty region could exist. The prevailing theories of cosmic evolution suggested that matter should be distributed more evenly throughout space, with only small variations in density. The Boötes Void challenged these assumptions, presenting a cosmic mystery that continues to puzzle astronomers today. One leading theory suggests that this void formed in the early universe when quantum fluctuations created regions of slightly lower density. Over billions of years, gravity pulled matter away from these underdense regions and toward areas of higher density, gradually expanding the voids and concentrating matter into the cosmic web of filaments and clusters we observe today. The Boötes Void represents an extreme example of this process, a region where the universe's construction project simply left behind an enormous empty lot. The few galaxies that do inhabit this cosmic wilderness show signs of their isolation. Many appear younger and smaller than galaxies found in denser regions of space, suggesting that the lack of neighboring galaxies has affected their evolution. Without the gravitational interactions and galactic mergers that drive star formation in more crowded cosmic neighborhoods, these void galaxies have lived relatively quiet, undisturbed lives. For any hypothetical traveler venturing into the Boötes Void, the experience would be profoundly isolating. Looking up at the night sky from a planet within this region, you would see almost no galaxies at all. The familiar cosmic landmarks that help us navigate the universe would be absent, replaced by an endless expanse of dark sky, punctuated only by the faint glow of the most distant quasars at the very edge of the observable universe. The temperature within the void hovers at approximately 2.7 Kelvin, just barely above absolute zero. This is the cosmic microwave background radiation, the afterglow of the Big Bang that permeates all of space. Here, in this cosmic emptiness, it represents virtually the only source of energy, creating an environment of almost perfect stillness and cold. Yet, even in this apparent nothingness, the universe continues its subtle work. Dark matter, that mysterious substance that outweighs ordinary matter 5 to 1, still threads through the void in invisible filaments. Dark energy, the force driving the universe's accelerating expansion, continues its relentless push, slowly stretching the void even larger over cosmic time. The Boötes Void serves as a cosmic laboratory, offering scientists a glimpse into what the universe might have looked like in its youth. before gravity had time to sculpt the elaborate structures we see today. It reminds us that space itself is not merely empty, but actively empty, carved out by the fundamental forces that shape our cosmos. Recent studies using advanced computational models have revealed that the Boötes Void is not completely uniform in its emptiness. Within this cosmic desert, there exist even smaller voids, creating a fractal-like structure of emptiness within emptiness. These sub-voids, some spanning tens of millions of light-years, suggest that the process of cosmic evacuation operates on multiple scales simultaneously. The gravitational effects of the void extend far beyond its boundaries. Galaxies approaching the void's edge experience a phenomenon called the void effect, where the lack of gravitational pull from within actually accelerates their motion away from the void. This creates a subtle but measurable influence on the cosmic flow of matter, like a gravitational anti-magnet pushing neighboring galaxies toward denser regions of space. Scientists have also discovered that the cosmic microwave background radiation appears slightly cooler when observed through the void. This effect, known as the integrated Sachs-Wolf effect, occurs because photons from the early universe lose energy as they climb out of gravitational wells. In the case of the Boötes Void, the opposite happens. Photons gain energy as they fall into this cosmic depression. But the overall effect still results in a measurable temperature difference. The existence of such massive voids has implications for our understanding of dark energy, the mysterious force driving the universe's accelerating expansion. Some theories suggest that regions like the Boötes Void might experience different rates of expansion than denser areas, creating a complex patchwork of cosmic expansion rates across the universe. This could help explain some of the discrepancies in measurements of the Hubble constant, the rate at which the universe is expanding. For astronomers studying galaxy formation and evolution, the Boötes Void represents a control group in a cosmic experiment. By comparing the few galaxies within the void to those in normal density regions, scientists can isolate the effects of environment on galactic development. They have found that void galaxies tend to be more gas-rich and have higher rates of star formation relative to their mass, suggesting that the peaceful environment allows them to retain more of their primordial material. The void also serves as a natural telescope, its emptiness providing an unobstructed view to the most distant reaches of the universe. Astronomers can peer through this cosmic window to observe galaxies and quasars that might otherwise be hidden behind the gravitational lensing effects of intervening matter. In this way, the Great Nothing becomes a valuable tool for exploring the something that lies beyond. Perhaps most remarkably, the Boötes Void challenges our intuitive understanding of what constitutes real in the universe. While we often think of matter and energy as the fundamental reality, voids like this remind us that the absence of matter is equally important in shaping cosmic structure. The void's emptiness is not accidental, but necessary, carved out by the same physical laws that create galaxies and stars. As you contemplate this vast cosmic emptiness, consider that its very existence tells us something profound about the nature of space and time. The void's boundaries are not walls, but gradual transitions, places where the sparse matter within slowly gives way to the richer galactic neighborhoods beyond. It represents a cosmic pause in the universe's grand symphony, a moment of silence that makes the surrounding music all the more meaningful. In the end, the Boötes Void stands as one of the universe's most paradoxical creations, a place defined entirely by what it lacks, yet somehow more remarkable than regions filled with countless stars and galaxies. It is a reminder that even nothing, when stretched across such cosmic scales, becomes something magnificent and strange, a testament to the universe's capacity for creating wonders from the simplest of ingredients: space, time, and the gentle pull of gravity across eons. The surface of a neutron star. Picture standing on a surface so dense that a teaspoon of its material would weigh as much as Mount Everest. Welcome to the surface of a neutron star, where the very atoms that make up ordinary matter have been crushed beyond recognition, creating one of the most extreme environments in the known universe. Neutron stars are the collapsed cores of massive stars that have exhausted their nuclear fuel and exploded as supernovae. What remains is a sphere typically only 12 miles across, yet containing more mass than our entire sun. This compression is so extreme that the star's matter exists in a state unlike anything found on Earth, where the fundamental building blocks of atoms have been forced into configurations that stretch the boundaries of physics itself. The surface gravity on a neutron star is approximately 200 billion times stronger than Earth's gravity. If you could somehow survive the journey to this stellar remnant, your weight would increase by a factor that defies comprehension. A person weighing 150 pounds on Earth would weigh 30 trillion pounds on a neutron star's surface. The gravitational pull is so intense that it warps space and time around the star, creating effects that Einstein's theories predict, but that exist nowhere else in such extremity. The surface itself presents a landscape of crystalline perfection and mathematical beauty. The outer crust consists of atomic nuclei arranged in a perfectly ordered lattice structure, more regular and precise than any crystal found in nature. These nuclei, stripped of their electrons by the immense pressure, form geometric patterns that extend across the entire surface. The regularity is so perfect that the surface can be thought of as a single, star-sized crystal, harder than diamond and stronger than steel by factors of billions. Temperature variations across this surface tell a story of cosmic violence and gradual cooling. A newly formed neutron star burns at temperatures exceeding 1 million Kelvin, hot enough to emit X-rays that can sterilize planets dozens of light years away. Over millions of years, this temperature slowly decreases, but even ancient neutron stars maintain surface temperatures of around 100,000 Kelvin, making them eternally incandescent beacons in the cosmic darkness. The magnetic field surrounding a neutron star creates an environment of unimaginable intensity. These fields can be trillions of times stronger than Earth's magnetic field, powerful enough to distort the very atoms that venture near. On the surface, this magnetism shapes the behavior of any remaining matter, creating channels and streams where charged particles flow in perfectly ordered patterns. The magnetic field lines emerge from the star's surface like invisible threads, extending far into space and creating the lighthouse-like beams we observe as pulsars. What makes the neutron star surface truly alien is the nature of matter itself at these densities. The normal boundaries between atomic nuclei break down completely. Instead of distinct atoms separated by empty space, the surface consists of a sea of neutrons packed so tightly that they touch one another. This neutron fluid behaves according to quantum mechanical principles scaled up to macroscopic sizes, creating a substance that is simultaneously liquid and solid, flowing yet crystalline. Mountains on a neutron star's surface, if they exist at all, would be microscopic by astronomical standards, yet massive beyond terrestrial comparison. The immense gravity ensures that no surface irregularity can exceed more than a few millimeters in height before the gravitational force overcomes the crystalline strength of the neutron matter. These tiny mountains would contain more mass than Earth's largest mountain ranges, compressed into structures smaller than a grain of sand. The atmosphere above this surface, when it exists, consists of elements in their most exotic states. Hydrogen and helium, if present, exist as a thin plasma layer only centimeters thick. The intense gravity compresses this atmosphere so severely that its density can exceed that of water on Earth. Yet it remains gaseous due to the extreme temperatures. Light passing through this atmosphere becomes distorted and focused by the gravitational lensing effects, creating a natural lens that bends starlight in complex patterns. Starquakes represent another extraordinary phenomenon unique to neutron star surfaces. As these stellar remnants gradually slow their rotation over millions of years, the crystalline crust adjusts to the changing shape, occasionally fracturing with tremendous force. These starquakes release more energy in a fraction of a second than our sun produces in an entire year, causing the entire star to ring like a cosmic bell with vibrations that propagate through the dense matter at near-light speeds. The rotation of many neutron stars adds another layer of complexity to their surface environment. Some neutron stars spin hundreds of times per second, creating centrifugal forces that compete with the immense gravitational pull. This rotation can cause the star to bulge slightly at its equator and creates patterns of stress and strain in the crystalline surface that shift and evolve with mathematical precision. The boundary between the neutron star's surface and space itself blurs in fascinating ways. The intense gravitational field creates what physicists call a photon sphere, a region where light can actually orbit the star. Photons traveling tangentially to the surface at just the right distance will circle the neutron star indefinitely, creating ghost images and optical illusions that make the boundary between the star and the surrounding vacuum unclear and dreamlike. For any theoretical observer on such a surface, the view of the surrounding universe would be profoundly altered. The intense gravitational field would bend light from distant stars, creating multiple images of the same celestial objects and distorting the familiar patterns of constellations beyond recognition. The neutron star's rapid rotation would cause this cosmic panorama to wheel overhead at dizzying speeds, while the star's magnetic field would paint the sky with auroras of unimaginable intensity and beauty. The surface serves as a boundary between two realms: the exotic interior, where matter exists in states that challenge our understanding of physics, and the vacuum of space, where the star's influence extends through gravity and magnetism across light years. This boundary represents a place where the universe's most extreme forces converge with an intensity found nowhere else in nature, creating a laboratory where the deepest mysteries of physics play out on a stage barely larger than a terrestrial city. Inside a black hole, journey with us into the ultimate cosmic mystery, a place where space and time themselves break down and the very laws of physics reach their limits. Inside a black hole lies the singularity, a point of infinite density that represents perhaps the strangest destination in the universe, yet one that no traveler can ever truly reach or return from to tell the tale. To understand this paradoxical realm, we must first grasp what happens as you approach a black hole's event horizon. This invisible boundary marks the point of no return, where the gravitational pull becomes so strong that not even light can escape. Yet crossing this threshold would feel surprisingly ordinary to you as the falling observer. You would pass through without sensing any particular moment of transition, unaware that you had just entered a region of space from which there is no escape. The journey inward reveals one of the universe's most profound paradoxes. As you fall toward the center, time itself becomes your enemy and your salvation simultaneously. From your perspective, everything proceeds normally. You continue falling at an accelerating pace, watching the curved walls of space-time close in around you. Minutes pass, then hours, as you plummet toward the singularity at the black hole's heart. But to an outside observer watching your descent, your journey takes on an entirely different character. They would see you slowing down as you approach the event horizon, your image becoming redder and dimmer as the black hole's gravity stretches the light waves carrying your image. From their perspective, you would appear to freeze at the event horizon, your final moments stretched across eternity, never quite reaching that point of no return. This is the magic and mystery of relativity made manifest. Two observers experiencing the same event, yet witnessing completely different realities, both equally valid within their own reference frames. You fall through in finite time while simultaneously taking forever to cross the boundary. A cosmic riddle that demonstrates how malleable our concepts of space and time truly are. As you continue your inward journey, the tidal forces begin to make themselves known. These forces arise because gravity is stronger at your feet than at your head, creating a stretching effect that gradually grows more pronounced. In a stellar mass black hole, this stretching would become extreme quite quickly, elongating your body in a process astronomers have dubbed spaghettification. However, in a supermassive black hole, millions of times more massive than our sun, these forces remain gentle for much longer, allowing a more leisurely exploration of this strange realm. The space around you begins to exhibit properties that challenge every intuition about geometry and direction. Inside the event horizon, all paths lead inward toward the singularity. There is no direction you can turn, no trajectory you can follow that leads anywhere but deeper into the black hole's interior. The very concept of up and down loses meaning as the curvature of space-time becomes so extreme that all directions point toward the center. Light behaves strangely in this environment, creating a surreal visual landscape. Photons that entered the black hole before you can overtake you on their own journey inward, creating ghostly images of the black hole's past. You might see light that has been trapped, circling the black hole's interior in complex orbits, carrying images of matter that fell in long ago. The visual experience becomes a time machine of sorts, displaying the black hole's history in layers of light. The singularity itself represents the ultimate destination of your journey, yet it remains forever mysterious. Current physics describes it as a point of infinite density and zero volume, where the curvature of space-time becomes infinite and our mathematical tools simply break down. At this point, the very concepts of space and time lose their meaning, and the laws of physics as we understand them cease to apply. Some theories suggest that the singularity might not be a point at all, but rather a region where quantum effects become dominant, preventing the formation of true mathematical infinity. These quantum theories propose that matter might be compressed to incredible but finite densities, creating exotic states of matter that exist nowhere else in the universe. In these models, the singularity becomes a realm where the quantum mechanical and gravitational worlds merge in ways we cannot yet comprehend. The interior of a black hole might also harbor phenomena that violate our everyday understanding of causality. Some solutions to Einstein's equations suggest the possibility of closed time-like curves within black holes, regions where cause and effect become tangled and time loops back on itself. These mathematical possibilities hint at a realm where the normal flow of time breaks down completely. Recent theoretical work has explored the idea that black hole interiors might be connected to other regions of spacetime through structures called Einstein-Rosen bridges or wormholes. These hypothetical tunnels through spacetime could, in principle, connect the interior of one black hole to the interior of another, or even to a completely different universe. While these ideas remain highly speculative, they suggest that the interior of a black hole might serve as a gateway to realms beyond our observable cosmos. The information paradox adds another layer of mystery to the black hole interior. Quantum mechanics suggests that information cannot be destroyed, yet anything that falls into a black hole appears to be lost forever. This paradox has led some physicists to propose that the interior of a black hole might not exist at all in the way we imagine, but rather that information is somehow encoded on the black hole's surface in ways that preserve the quantum mechanical laws. The holographic principle suggests that all the information about the three-dimensional interior of a black hole might be encoded on its two-dimensional event horizon surface, much like a hologram encodes three-dimensional information on a flat surface. This radical idea implies that what we perceive as the interior might be an emergent property, a kind of holographic projection created by information processing on the boundary. Temperature gradients within the black hole create another fascinating aspect of this environment. While the event horizon itself has a temperature inversely related to the black hole's mass, the interior experiences complex thermal dynamics. Hawking radiation, the theoretical emission of particles from the black hole's surface, suggests that black holes slowly evaporate over time, with smaller black holes radiating more intensely than larger ones. The geometry inside a black hole also exhibits properties that challenge our understanding of space itself. Distance measurements become ambiguous when space-time is curved to such extremes. The concept of how far you are from the singularity becomes meaningless in conventional terms, as the metric of space itself is distorted beyond normal comprehension. Parallel lines converge, and the shortest distance between 2 points may involve paths that seem counterintuitive. Virtual particles and quantum fluctuations take on new significance in the black hole's interior. The intense gravitational fields can separate virtual particle pairs that normally annihilate each other almost instantly, potentially creating real particles from the quantum vacuum. These quantum effects might become increasingly important as you approach the singularity, where the boundary between the classical and quantum worlds dissolves entirely. As your journey continues toward the singularity, you enter a realm where the very fabric of reality becomes uncertain. Time and space might fragment into discrete, quantized units. The smooth continuum of space-time might reveal itself to be an illusion, breaking down into a foam-like structure at the smallest scales. Here, at the boundary between the known and the unknowable, physics itself becomes a work in progress. The final approach to the singularity represents humanity's ultimate frontier, a place where our current understanding of reality reaches its absolute limits. Whether the singularity represents a point of infinite density, a quantum realm of exotic matter, or something else entirely beyond our current imagination, it stands as the universe's greatest mystery, forever hidden behind the event horizon, forever beyond the reach of any observer who hopes to return and share the tale. A rogue planet. Imagine a world cast out from its solar system, sentenced to wander the galaxy in perpetual darkness. Welcome to a rogue planet, one of the universe's most solitary travelers, drifting through the cosmic void without the warmth of a star to call home. These planetary outcasts represent some of the loneliest places in the universe, yet they harbor secrets that challenge our understanding of where life might exist. Rogue planets are worlds that have been ejected from their original solar systems through gravitational interactions, often during the chaotic early periods of planetary formation. When multiple planets orbit a young star, their gravitational influences can create instabilities that send one or more worlds careening into interstellar space. Others may form in isolation, condensing from gas and dust in regions too sparse to create a star, becoming planets that never knew the embrace of stellar light. The journey of a rogue planet through interstellar space is one of profound isolation. These worlds travel at speeds of tens of kilometers per second, crossing the vast distances between stars over millions of years. Their paths are determined by the gravitational pull of the galaxy itself, following orbits around the Galactic Center that take hundreds of millions of years to complete. Unlike planets in stable solar systems, rogue planets experience no seasons, no day-night cycles, and no variation in their cosmic environment save for the slow drift of distant stars across their skies. The surface of a rogue planet presents a landscape of eternal winter. Without a star to provide heat, these worlds quickly radiate away any warmth they once possessed, cooling to temperatures that hover just above absolute zero. The atmosphere, if one exists, may freeze and fall to the surface as snow, creating landscapes covered in nitrogen ice, frozen carbon dioxide, or crystallized methane depending on the planet's original composition. Yet beneath this frozen exterior, some rogue planets may harbor surprising warmth. Radioactive decay within the planet's core continues regardless of external temperature, generating heat that can persist for billions of years. Large rogue planets might retain enough internal heat to maintain liquid water oceans beneath thick shells of ice, similar to the subsurface oceans found on Jupiter's moon Europa. These hidden seas could remain liquid for geological ages, creating potential havens for life in the most unlikely of places. The gravitational effects experienced by a rogue planet create unique environmental conditions. Freed from the tidal forces of a nearby star, these worlds spin according to the angular momentum they carried from their formation. Some might rotate rapidly, creating strong centrifugal forces that flatten their shape and generate powerful magnetic fields. Others might tumble chaotically through space, their rotational axes shifting over time as they encounter the gravitational influences of passing stars or molecular clouds. The magnetic field of a rogue planet, if it possesses one, serves as its only shield against the harsh radiation of interstellar space. Cosmic rays, high-energy particles, accelerated by distant supernovae and other cosmic events, constantly bombard these solitary worlds. A strong magnetic field can deflect these particles, creating auroras that dance across the planet's dark skies in brilliant displays of green, blue, and red light. These auroras might be the only source of illumination on an otherwise dark world, painting the frozen landscape in ethereal colors. The chemical evolution of rogue planets follows paths unknown on worlds that orbit stars. Without the energy input from stellar radiation, chemical processes slow to a crawl in the frozen surface layers. However, the interface between the frozen surface and any subsurface ocean becomes a laboratory for exotic chemistry. Temperature gradients, pressure variations, and the presence of dissolved minerals create conditions where complex organic molecules might form and evolve. Even in the absence of sunlight, some rogue planets may retain moons from their original solar system, creating miniature gravitational systems that drift through interstellar space. These moon systems can generate tidal heating through their gravitational interactions, providing additional energy sources that could maintain liquid water or drive geological activity. The tidal forces between a rogue planet and its moons might create fractures in ice shells, allowing material exchange between surface and subsurface environments. The discovery of rogue planets has revolutionized our understanding of planetary formation and distribution throughout the galaxy. Current estimates suggest there may be billions of these wandering worlds in our galaxy alone, possibly outnumbering stars. They represent a hidden population of planets that exists in the dark spaces between stellar systems, invisible except when they occasionally pass in front of distant stars or cause gravitational lensing effects that briefly magnify background starlight. The potential for life on rogue planets opens new chapters in astrobiology. Life forms that might evolve in the subsurface oceans of these worlds would be entirely independent of stellar energy, relying instead on chemical processes and geothermal activity. Such organisms might be similar to the extremophile bacteria found near deep-sea hydrothermal vents on Earth, creatures that derive energy from chemical reactions rather than photosynthesis. The long-term fate of rogue planets varies depending on their mass and the galaxy's evolution. Smaller worlds gradually cool and become completely frozen, while larger planets might maintain active geology for billions of years. Some rogue planets might eventually be captured by passing star systems, becoming new members of stellar families, and potentially experiencing a renaissance as their frozen surfaces begin to thaw under the warmth of their adopted star. The study of rogue planets also provides insights into the violent early history of solar systems. Computer simulations suggest that our own solar system likely ejected several planets during its formation, sending worlds that might have harbored early life into the cosmic wilderness. These ejected siblings of Earth now wander the galaxy, carrying with them the chemical signatures and possibly even the biological heritage of our solar system's youth. For any hypothetical explorer visiting a rogue planet, the experience would be profoundly different from exploring worlds that orbit stars. The landscape would be illuminated only by starlight and cosmic rays, creating a twilight environment where familiar landmarks would be bathed in the dim glow of distant suns. The absence of weather patterns driven by stellar heating would create stable but alien atmospheric conditions, where the only winds might be generated by the planet's rotation or the sublimation of surface ices. The night sky from a rogue planet would offer an unparalleled view of the galaxy. Without the glare of a nearby star, distant galaxies and nebulae would be visible in stunning detail, creating a cosmic panorama that changes slowly over millennia as the planet drifts through different regions of interstellar space. These wandering worlds serve as natural observatories, providing perspectives on the universe that are impossible to achieve from planets bound to stellar systems. In the end, rogue planets represent the universe's ultimate survivors, worlds that have learned to exist independently of the stellar nurseries where most planets spend their entire existence. They embody a form of planetary resilience and adaptability that expands our concept of where worlds can exist and where life might find a way to flourish, even in the seemingly empty spaces between the stars. A quasar's core, deep in the heart of distant galaxies, billions of light years from Earth, lies one of the universe's most spectacular and violent theaters. Welcome to the core of a quasar, where a supermassive black hole feeds with unprecedented fury, transforming matter into energy with an efficiency that outshines entire galaxies. This is a realm where gravity, magnetism, and radiation converge to create the most luminous, sustained phenomena in the known universe. At the center of this cosmic maelstrom sits a supermassive black hole, containing the mass of millions or even billions of suns, compressed into a region smaller than our solar system. Unlike the stellar mass black holes formed from collapsed stars, these giants have grown over billions of years by consuming gas, dust, and entire stars that venture too close to their gravitational embrace. The black hole itself remains invisible, defined only by its event horizon, but its presence orchestrates a symphony of destruction and creation that can be observed across cosmic distances. Surrounding this central monster lies the accretion disk, a swirling maelstrom of matter spiraling inexorably toward its doom. This disk extends for light years in all directions, containing more mass than thousands of star systems. As material from the surrounding galaxy falls toward the black hole, it forms this vast, flattened structure that rotates with increasing velocity as it approaches the event horizon. The inner regions of the disk spin at significant fractions of the speed of light, creating conditions of temperature and pressure that exist nowhere else in the universe. The process of accretion transforms gravitational potential energy into heat and light with extraordinary efficiency. As matter spirals inward, friction between different layers of the disk heats the material to temperatures exceeding millions of degrees. At these temperatures, hydrogen and helium become fully ionized plasma, and the disk begins to glow with the intensity of billions of stars. The innermost regions reach temperatures of over 100 million Kelvin, hot enough to emit X-rays and gamma rays that can sterilize entire star systems. Magnetic fields threading through the accretion disk create additional complexity in this already extreme environment. These fields, generated by the motion of charged particles in the plasma, become twisted and amplified by the disk's differential rotation. The magnetic field lines act like invisible cables, channeling energy and matter in ways that shape the entire structure. Where these field lines become tangled and reconnect, they release enormous bursts of energy that add to the quasar's already tremendous luminosity. The temperature gradients within the accretion disk create a rainbow of radiation across the electromagnetic spectrum. The cooler outer regions, still thousands of times hotter than the surface of the sun, emit primarily an infrared and visible light. Moving inward, the temperature increases dramatically, shifting the peak emission through ultraviolet and into X-ray wavelengths. The very center of the disk, where matter makes its final plunge toward the black hole, blazes with gamma rays so energetic they can penetrate through light years of intervening matter. Perhaps the most spectacular feature of an active quasar core is the formation of relativistic jets. These narrow beams of particles and energy extend thousands of light years from the black hole's poles, traveling at speeds approaching that of light itself. The jets form when magnetic field lines become so twisted and compressed that they act like cosmic particle accelerators, launching material away from the black hole with tremendous velocity. These jets can extend far beyond the host galaxy, creating radio lobes that dwarf the stellar population that feeds the central engine. The environment near the black hole's event horizon represents one of the most extreme laboratories in physics. Space and time become severely warped by the intense gravitational field, causing clocks to run slower and distances to contract in ways that would seem impossible under ordinary circumstances. Light emitted from the inner edge of the accretion disk becomes gravitationally redshifted, losing energy as it climbs out of the black hole's gravitational well. Some photons become trapped in unstable orbits around the black hole, circling multiple times before either falling in or escaping to space. The feeding patterns of supermassive black holes follow cycles that span millions of years. During active phases, the black hole consumes material at rates equivalent to several Earth masses per second, powering the brilliant quasar phenomenon. These feeding frenzies are often triggered by galactic mergers or close encounters that funnel gas and stars toward the central black hole. Between these active periods, the black hole may lie dormant for millions of years, waiting for the next cosmic meal to arrive. The accretion process also generates powerful winds that sweep outward from the disk at speeds of thousands of kilometers per second. These winds carry away a significant fraction of the infalling material, creating a self-regulating mechanism that prevents the black hole from consuming matter too rapidly. The winds interact with the surrounding interstellar medium, creating shock waves that heat and ionize gas across vast regions of the host galaxy. Within the innermost stable circular orbit, matter experiences its final moments before crossing the event horizon. This region, only a few times larger than the black hole itself, represents the point of no return for infalling material. Here, the orbital velocity approaches the speed of light, and tidal forces begin to dominate over pressure forces within individual particles. Matter in this region emits its final photons before disappearing forever behind the event horizon. The study of quasar cores has revealed fundamental insights about the relationship between supermassive black holes and their host galaxies. The mass of the central black hole appears to be intimately connected to the properties of the surrounding galaxy, suggesting that these cosmic monsters play a crucial role in regulating star formation and galactic evolution. The energy output from active galactic nuclei can halt star formation across entire galaxies, creating a feedback mechanism that shapes the large-scale structure of the universe. The variability of quasar emission provides a window into the chaotic dynamics of the accretion process. Brightness changes on timescales from hours to years reflect fluctuations in the rate at which matter falls into the black hole. These variations can be caused by instabilities in the accretion disk, the disruption of individual stars that wander too close, or changes in the magnetic field configuration that affect the efficiency of energy extraction. For any hypothetical observer brave enough to venture near a quasar's core, the experience would be one of overwhelming luminosity and energy. The radiation field would be so intense that matter itself would be ionized and accelerated to relativistic speeds. Time dilation effects would become extreme, causing the outside universe to appear to speed up dramatically, while local processes seem to slow down. The boundary between matter and energy would blur, as the intense radiation field converts particles into pure electromagnetic energy. The quasar core represents nature's most efficient engine, converting matter into energy with the efficiency that far exceeds nuclear fusion. It stands as a testament to the universe's capacity for creating beauty from violence, light from darkness, and order from chaos, demonstrating that even in the most extreme environments, the fundamental laws of physics continue to operate with mathematical precision and cosmic elegance. The Great Attractor. In the depths of space, hidden behind the dust and stars of our own Milky Way galaxy, lies one of the cosmos's most enigmatic phenomena. The Great Attractor exerts a gravitational pull so immense that it draws our entire local group of galaxies, along with thousands of others, toward a region of space we can barely see. This invisible titan represents one of the universe's greatest mysteries, a cosmic force that shapes the motion of matter across hundreds of millions of light years. The discovery of the Great Attractor emerged from careful observations of cosmic microwave background radiation and galaxy motion studies conducted in the 1970s and 1980s. Astronomers noticed that our local group, which includes the Milky Way, Andromeda, and dozens of smaller galaxies, was moving through space at approximately 600 kilometers per second, in a direction that couldn't be explained by the gravitational influence of known nearby structures. Something massive was pulling us, along with thousands of neighboring galaxies, toward a region in the constellation Centaurus. What makes the Great Attractor particularly mysterious is its location in what astronomers call the zone of avoidance. This region lies directly behind the plane of our galaxy, where thick clouds of dust and the dense concentration of foreground stars make it nearly impossible to observe distant objects. The Milky Way's disk effectively blocks our view of this cosmic phenomenon, leaving astronomers to deduce its properties through indirect methods and the subtle gravitational effects it exerts on surrounding matter. The gravitational influence of the Great Attractor extends across a region approximately 500 million light-years in diameter, encompassing tens of thousands of galaxies in what's known as the Great Attractor flow. These galaxies, including our own, are being drawn toward this massive concentration of matter at speeds that suggest the presence of something equivalent to tens of thousands of galaxy masses, concentrated in a relatively small region of space. The scale of this gravitational influence rivals that of the largest known structures in the universe. Recent studies using infrared and radio telescopes, which can penetrate the dust of our galaxy's disk, have begun to reveal the true nature of this cosmic mystery. The Great Attractor appears to be associated with a massive galaxy cluster called the Norma Cluster, along with several other large galaxy clusters and superclusters that together form a concentration of matter dense enough to explain the observed gravitational effects. However, even this revealed structure may not account for the full strength of the gravitational pull. The concept of dark matter plays a crucial role in understanding the Great Attractor's influence. Like all large-scale structures in the universe, this region likely contains far more dark matter than visible matter, with the unseen material providing most of the gravitational force that attracts distant galaxies. The dark matter forms a vast cosmic web of filaments and nodes, with the Great Attractor representing one of the most massive intersections in this invisible scaffolding that underlies all cosmic structure. The motion of our local group toward the Great Attractor has profound implications for our cosmic address. We are not simply orbiting within our galaxy or moving randomly through space, but participating in a vast cosmic dance orchestrated by gravity on the largest possible scales. Our trajectory carries us at hundreds of kilometers per second toward this distant region, a journey that will take billions of years to complete, if it ever does. The Great Attractor's influence competes with other large-scale motions in our cosmic neighborhood. Beyond the Great Attractor lies an even larger structure called the Shapley Supercluster, which may be partially responsible for our local group's motion. Some astronomers suggest that what we observe as the Great Attractor effect might actually be the combined gravitational influence of multiple massive structures aligned along our line of sight, creating a gravitational highway that channels galaxy motion across vast distances. The study of the Great Attractor has revealed important insights about the large-scale structure of the universe. It demonstrates that matter is not distributed uniformly through space, but is organized into an intricate cosmic web of filaments, sheets, and nodes separated by vast empty voids. The Great Attractor represents one of the most massive nodes in this web, a place where multiple filaments of dark matter converge to create a gravitational nexus of extraordinary power. Temperature maps of the cosmic microwave background radiation show subtle imprints of the Great Attractor's influence. The radiation appears slightly cooler in the direction of the Great Attractor due to the gravitational redshift effect, where photons lose energy as they climb out of gravitational wells. This effect, known as the integrated Sachs-Wolf effect, provides independent confirmation of the Great Attractor's mass and influence. The region around the Great Attractor exhibits unique properties in terms of galaxy evolution and star formation. Galaxies falling into such massive gravitational wells experience environmental effects that can trigger or suppress star formation depending on their specific circumstances. The intense gravitational interactions can strip gas from smaller galaxies while simultaneously compressing gas in others, leading to bursts of stellar birth that illuminate the cosmic web with new stars. Modern computer simulations of cosmic evolution consistently reproduce structures similar to the Great Attractor, suggesting that such massive gravitational concentrations are natural outcomes of the universe's evolution under the influence of dark matter and dark energy. These simulations show that the cosmic web we observe today grew from tiny quantum fluctuations in the early universe, amplified over billions of years by gravitational collapse and expansion. The Great Attractor also serves as a cosmic laboratory for testing our understanding of gravity on the largest scales. The observed motions of galaxies in its vicinity provide tests of Einstein's general relativity and alternative theories of gravity. So far, the observed effects match the predictions of general relativity remarkably well, supporting our current understanding of how gravity operates across cosmic distances. Future observations promise to reveal more details about the Great Attractor's structure and composition. Advanced infrared telescopes and gravitational wave detectors may eventually provide direct observations of this hidden region, while improved measurements of galaxy motions will refine our understanding of its mass and extent. These studies will help determine whether the Great Attractor is a single massive structure or a complex of multiple clusters and superclusters aligned along our line of sight. The existence of the Great Attractor raises profound questions about the ultimate fate of our cosmic neighborhood. As galaxies continue to fall toward this massive concentration, they will eventually merge and coalesce, possibly forming one of the largest bound structures in the universe. However, the accelerating expansion of space driven by dark energy may prevent the most distant galaxies from ever reaching their gravitational destination, leaving them frozen in their approach as space itself expands faster than they can fall inward. For any hypothetical observer positioned near the Great Attractor, the view would be spectacular beyond imagination. The concentration of galaxies would create a brilliant cosmic metropolis, with galaxy clusters packed more densely than anywhere else in the observable universe. The gravitational lensing effects would distort and magnify the images of even more distant galaxies, creating a natural telescope that reveals the deepest structures of the cosmos. The Great Attractor stands as a reminder that our universe is shaped and sculpted by forces operating on scales almost beyond human comprehension. It represents the invisible architecture that underlies all cosmic structure, demonstrating that even the largest galaxies are merely components in an even grander design, drawn together by gravity across billions of years to create the magnificent cosmic web that defines our universe's largest scale organization, Titan's methane lakes. Journey with us to the shores of an alien sea, where liquid methane laps against crystalline ice beaches beneath skies the color of burnt orange. Welcome to Titan, Saturn's largest moon and the only other world in our solar system known to harbor stable bodies of liquid on its surface. Here, in temperatures cold enough to freeze nitrogen, a complex hydrological cycle operates using hydrocarbons instead of water, creating landscapes that are both eerily familiar and utterly alien. Titan's methane lakes represent one of the most remarkable discoveries of planetary science, revealing a world where the basic chemistry of Earth's water cycle has been replaced by something entirely different, yet surprisingly analogous. These lakes, seas, and rivers contain liquid methane and ethane, hydrocarbons that exist as gases in Earth's atmosphere, but become liquid in Titan's frigid environment, where surface temperatures hover around -179 degrees Celsius. The largest of these alien seas, Kraken Mare, rivals the size of the Caspian Sea on Earth, stretching across hundreds of thousands of square kilometers of Titan's northern polar region. Its shores are defined not by sandy beaches, but by landscapes of water ice as hard as granite, sculpted by eons of hydrocarbon erosion into shapes that mirror terrestrial coastlines. The sea itself reaches depths of several hundred meters, creating a vast reservoir of liquid methane that represents one of the most substantial bodies of liquid in the outer solar system. The formation of Titan's methane lakes involves processes that echo Earth's own hydrological systems, while operating under entirely different chemical and physical conditions. Methane evaporates from the surface into Titan's thick atmosphere, where it condenses into clouds and eventually falls as rain. This methane precipitation carves river channels, fills lake basins, and creates seasonal variations in liquid levels that mirror the patterns we observe in terrestrial water bodies, albeit over much longer time scales. The atmospheric pressure on Titan's surface is about 50% greater than Earth's, creating conditions where liquid methane can exist stably at the surface without immediately boiling away. This dense atmosphere, composed primarily of nitrogen with a significant methane component, creates a greenhouse effect that helps maintain temperatures suitable for liquid hydrocarbons. The atmosphere's thickness also allows for complex weather patterns, including methane storms that can dump liquid hydrocarbons across vast areas of the moon's surface. The chemistry of Titan's lakes reveals a complex mixture of hydrocarbons that varies seasonally and geographically. While methane dominates in many regions, ethane becomes more concentrated in certain lakes, particularly those that have experienced significant evaporation. The dissolved nitrogen in these lakes creates solutions with properties unlike any natural liquids found on Earth, with viscosities and surface tensions that would produce unique fluid dynamics and wave patterns. Seasonal changes on Titan occur over Saturn's 29-year orbital period, creating long-term variations in the distribution and composition of surface liquids. During Titan's spring and summer in the northern hemisphere, increased solar heating drives evaporation from the polar lakes, while autumn and winter bring methane precipitation that refills the depleted basins. These seasonal cycles transport hydrocarbons across vast distances, creating a global circulation pattern that redistributes organic compounds around the moon. The shorelines of Titan's methane lakes exhibit features that would be recognizable to any terrestrial geologist, yet formed through entirely different processes. Erosional features carved by liquid methane create channels, deltas, and bay systems that mirror those found along Earth's coastlines. The interaction between liquid hydrocarbons and the ice rock substrate creates unique geological formations, including features that may represent hydrocarbon karst systems, where liquid methane has dissolved subsurface deposits of organic compounds. Wave action on Titan's methane seas remains largely theoretical, but fascinating to contemplate. The combination of low gravity, dense atmosphere, and the physical properties of liquid methane would create wave dynamics unlike anything observed on Earth. Waves might propagate more slowly, but could potentially reach greater heights relative to the gravitational conditions, creating seascapes where the familiar physics of ocean waves operates under alien parameters. The subsurface of Titan beneath its methane lakes may harbor even more remarkable features. Evidence suggests that a subsurface ocean of liquid water and ammonia exists deep beneath the moon's icy crust, separated from the surface methane lakes by dozens of kilometers of ice and rock. This creates a unique situation where two entirely separate liquid systems exist on the same world, one composed of hydrocarbons at the surface and another of water-ammonia solution in the deep interior. The organic chemistry occurring in and around Titan's methane lakes represents a natural laboratory for prebiotic chemical processes. The interaction between liquid hydrocarbons, atmospheric nitrogen, and energy sources such as cosmic radiation and lightning creates conditions where complex organic molecules can form and accumulate. These processes may be producing compounds similar to those that preceded the origin of life on Earth, making Titan's lakes invaluable for understanding how organic chemistry might evolve in environments very different from our own planet. The discovery of Titan's methane lakes has profound implications for our understanding of habitability in the outer solar system. While the surface conditions are far too cold and chemically exotic to support Earth-like life, the presence of stable liquids, complex organic chemistry, and energy sources creates environments where alternative forms of life might potentially exist. Some researchers have speculated about hypothetical organisms that could use liquid methane as a solvent instead of water, though such life forms would operate according to biochemical principles entirely different from terrestrial biology. The exploration of Titan's methane lakes by the Cassini-Huygens mission revealed surprising similarities to Earth's own lake systems, including seasonal variations, weather patterns, and geological processes that create familiar-looking landforms through alien chemistry. Radar observations showed lakes appearing and disappearing with seasonal changes, river systems flowing into larger bodies of liquid, and even what appear to be desert regions where ancient lake beds have dried up, leaving behind deposits of organic compounds. The interaction between Titan's methane lakes and its atmosphere creates a complex feedback system that regulates the moon's climate over geological timescales. The lakes serve as reservoirs that buffer atmospheric methane concentrations, preventing the atmosphere from either accumulating too much methane or losing it entirely to space. This regulatory mechanism has likely operated for millions of years, maintaining conditions suitable for liquid hydrocarbons despite the gradual evolution of Saturn's system and the solar system as a whole. Future missions to Titan may include boats designed to sail across these alien seas, submarines to explore their depths, and aircraft to survey the complex coastlines where liquid hydrocarbons meet solid ice. Such missions would provide unprecedented insights into the behavior of liquids under alien conditions and the potential for complex chemistry in environments vastly different from Earth. Standing on the shore of a Titan methane lake would present a sensory experience unlike anywhere else in the solar system. The orange sky would cast an eerie glow across the dark liquid surface, while the low gravity would allow for movements and gestures impossible on Earth. The sound of methane waves lapping against ice shores would carry differently through the dense atmosphere, creating acoustic environments as alien as the chemistry that sustains them. Titan's methane lakes remind us that the universe's capacity for creating familiar patterns through unfamiliar chemistry extends even to our own solar system. They represent a world where the cycles that sustain Earth's biosphere operate through entirely different materials, creating landscapes that are simultaneously recognizable and completely foreign, demonstrating that nature's fundamental processes can manifest in ways that challenge our terrestrial perspective while revealing the underlying unity of physical laws across diverse environments. The event horizon. Imagine approaching an invisible boundary in space, a threshold beyond which the very concept of escape loses all meaning. Welcome to the event horizon, the point of no return that surrounds every black hole like an imperceptible membrane between our universe and the unknown. This boundary represents one of the most profound concepts in physics, a place where space and time themselves conspire to create a one-way passage into mystery. The event horizon is not a physical surface in any conventional sense. but rather a mathematical boundary defined by the curvature of space-time around a black hole. Its location is determined by the Schwarzschild radius, a distance from the black hole's center where the escape velocity equals the speed of light. For a black hole with the mass of our Sun, this radius would be approximately 3 kilometers, while supermassive black holes can have event horizons larger than our solar system. What makes the event horizon truly remarkable is its asymmetric nature with respect to the flow of information and matter. From outside the black hole, nothing that crosses this boundary can ever send a signal back to the external universe. Light, radio waves, and any other form of electromagnetic radiation emitted from within the event horizon cannot overcome the gravitational pull to reach distant observers. This creates a cosmic censorship that forever hides the black hole's interior from the outside universe. The experience of crossing an event horizon would depend dramatically on your frame of reference. For someone falling toward the black hole, the crossing would occur at a specific moment in their personal timeline. Yet this moment would appear completely ordinary. There would be no physical barrier to breach, no sudden sensation of crossing a threshold. The falling observer would simply continue their journey inward, unaware that they had just passed the point beyond which return becomes impossible. However, for an external observer watching this descent, the story unfolds very differently. Due to the extreme gravitational time dilation near the event horizon, they would see the falling person slow down dramatically as they approach the boundary. The image of the falling observer would become increasingly redshifted, their light stretched to longer and longer wavelengths until it fades beyond detection. From the outside perspective, the falling person would appear to freeze at the event horizon, their final moments stretched across eternity. This paradox illustrates one of the most profound aspects of the event horizon. It represents a boundary not just in space, but in the nature of time itself. The horizon marks the transition between regions of space-time with fundamentally different causal structures. Outside the horizon, space-like and time-like directions maintain their familiar relationships. But inside, these relationships become inverted in ways that challenge our intuitive understanding of reality. The formation of an event horizon during stellar collapse represents one of nature's most dramatic phase transitions. As a massive star exhausts its nuclear fuel and begins to collapse, there comes a critical moment when the escape velocity at its surface equals the speed of light. At this instant, the event horizon forms, not gradually, but instantaneously across the entire spherical surface. This moment marks the birth of a black hole and the creation of a new region of space-time forever cut off from the rest of the universe. The geometry of space-time near an event horizon exhibits properties that seem to violate our everyday understanding of distance and direction. Inside the horizon, all paths lead inexorably toward the central singularity. The radial direction toward the black hole's center becomes time-like, meaning that falling inward becomes as inevitable as moving forward through time. Meanwhile, what were once space-like directions outside the horizon become time-like inside, creating a geometry where the normal relationships between space and time are fundamentally altered. Quantum mechanics introduces additional complexity to our understanding of event horizons through the phenomenon of Hawking radiation. According to quantum field theory, virtual particle pairs constantly appear and annihilate throughout empty space. Near an event horizon, the intense gravitational field can separate these pairs before they annihilate, with one particle falling into the black hole while the other escapes as real radiation. This process suggests that event horizons are not completely black, but emit a faint glow, with a temperature inversely related to the black hole's mass. The information paradox presents one of the most challenging puzzles associated with event horizons. Classical general relativity suggests that information falling through an event horizon is lost forever. Yet, quantum mechanics insists that information cannot be destroyed. This conflict has led to proposed solutions ranging from the idea that information is somehow encoded on the event horizon's surface to more radical suggestions that event horizons might not exist in the form that classical physics predicts. The study of event horizons has revealed connections between gravity, thermodynamics, and information theory that were previously unsuspected. Event horizons possess entropy proportional to their surface area rather than their volume, suggesting that the information content of a region of space might be fundamentally limited by the area of its boundary rather than its volume. This insight has profound implications for our understanding of the nature of space, time, and information. Rotating black holes introduce additional complexity to the structure of event horizons through the formation of the ergosphere, a region outside the event horizon where space-time itself is dragged around by the black hole's rotation. Within the ergosphere, it becomes impossible to remain stationary relative to distant observers, as the very fabric of space and time is carried along by the black hole's spin. This creates opportunities for energy extraction through processes that would be impossible near non-rotating black holes. The detection of gravitational waves from merging black holes has opened new windows into the behavior of event horizons during their most dynamic moments. When two black holes spiral together and merge, their individual event horizons undergo a complex dance of deformation and coalescence, eventually settling into the spherical form of the final merged black hole. These processes occur according to precise mathematical rules that demonstrate the remarkable predictive power of general relativity. For theoretical travelers approaching an event horizon, the experience would be profoundly influenced by the black hole's mass. Near stellar mass black holes, tidal forces would become extreme well before reaching the horizon, stretching and compressing matter in the process known as spaghettification. However, supermassive black holes have much gentler tidal forces at their event horizons, potentially allowing extended exploration of the boundary region before the inevitable journey to the central singularity. The event horizon represents more than just a mathematical curiosity or theoretical construct. It embodies some of the deepest questions about the nature of reality, the flow of time, and the fundamental limits of knowledge. It stands as a cosmic boundary that separates the knowable from the unknowable, the observable from the hidden, creating regions of the universe that remain forever beyond our reach, while simultaneously revealing the most profound truths about the cosmos through their very existence. In contemplating the event horizon, we encounter one of the universe's most perfect paradoxes, a boundary that is both absolutely fundamental to the structure of space-time and completely imperceptible to those who cross it. A threshold that represents both an ending and a beginning, a place where our understanding of physics reaches its current limits while pointing toward deeper truths yet to be discovered. The eye of the Helix Nebula. In the constellation Aquarius, approximately 650 light-years from Earth, lies one of the most haunting and beautiful sights in our galaxy. The Helix Nebula, often called the Eye of God, gazes back at us across the cosmic void with an eerily familiar appearance that has captivated astronomers and stargazers for generations. This celestial eye represents the final chapter in the life of a sun-like star, transformed into a glowing monument that will persist for thousands of years. The eye of the Helix Nebula began its existence as an ordinary star, similar to our own sun, but slightly more massive. For millions of years, this star burned hydrogen in its core, maintaining a delicate balance between the inward pull of gravity and the outward pressure of nuclear fusion. As the star aged, it gradually exhausted its hydrogen fuel and began the complex sequence of events that would eventually create the spectacular nebula we observe today. When the star's core hydrogen was depleted, it began fusing helium into heavier elements, causing the outer layers to expand dramatically. The star transformed into a red giant, swelling to hundreds of times its original size. During this phase, the star became unstable, pulsating and ejecting material in a series of stellar winds that carried away much of its mass. These expelled layers would eventually form the intricate structure of the nebula itself. The central cavity of the Helix Nebula, which creates the eye-like appearance, formed when the dying star shed its outer atmosphere in a relatively spherical shell. The intense ultraviolet radiation from the remaining stellar core ionizes the surrounding gas, causing it to glow with characteristic colors. Hydrogen emits a deep red light, while oxygen produces blue-green hues, creating the nebula's distinctive coloration that resembles a cosmic iris surrounded by glowing eyelids. What makes the Helix Nebula particularly striking is its apparent size in our sky. Spanning approximately half a degree, it appears larger than the full moon, though it is much fainter and requires telescopic observation to reveal its full glory. This impressive angular size, combined with its distance of 650 light-years, means the actual nebula measures about 2.5 light-years across, making it one of the nearest and largest planetary nebulae known to astronomers. The intricate structure of the nebula reveals itself through detailed observations across different wavelengths of light. The main ring appears smooth and uniform to the naked eye, but higher resolution images reveal a complex tapestry of braided filaments, knots, and streamers. These features result from instabilities in the stellar wind and interactions with the surrounding interstellar medium, creating patterns that evolve slowly over thousands of years. At the heart of this cosmic eye lies the remnant of the original star, now transformed into a white dwarf. This stellar corpse, no larger than Earth, but containing about 60% of the Sun's mass, burns at a surface temperature of approximately 120,000 Kelvin, making it one of the hottest known white dwarf stars. The intense radiation from this compact object powers the entire nebula, ionizing the surrounding gas and creating the luminous display that makes the structure visible across interstellar distances. The chemistry within the Helix Nebula tells the story of stellar nucleosynthesis, the process by which stars create heavy elements and distribute them throughout the galaxy. The nebular gas contains not only the hydrogen and helium that comprise the original star's outer layers, but also carbon, nitrogen, oxygen, and other elements forged in the star's core during its final evolutionary phases. These materials, enriched with the products of nuclear fusion, will eventually be incorporated into future generations of stars and planets. Temperature variations throughout the nebula create zones of different ionization and emission characteristics. The regions closest to the central white dwarf experience the most intense radiation, reaching temperatures of tens of thousands of degrees, and glowing primarily in high-energy ultraviolet and X-ray wavelengths. Further from the center, the gas cools and the emission shifts toward visible and infrared wavelengths, creating the layered appearance that contributes to the eye-like structure. The expansion velocity of the Helix Nebula provides insights into the timeline of its formation. The nebular material moves outward at approximately 31 kilometers per second, suggesting that the mass ejection events that form the nebula occurred roughly 10,600 years ago. This relatively recent formation, combined with the nebula's proximity to Earth, makes it an ideal laboratory for studying the late stages of stellar evolution and the physics of ionized gases in space. Observations of the Helix Nebula have revealed the presence of thousands of comet-like knots embedded within the larger structure. These dense condensations of gas and dust, each roughly the size of our solar system, appear to have formed through gravitational instabilities in the expanding shell. The knots show remarkable detail when observed with high-resolution telescopes, displaying heads pointing toward the central star and tails streaming away, creating the illusion of a swarm of cosmic tadpoles swimming through the nebular medium. The infrared emission from the Helix Nebula tells another part of its story, revealing the presence of molecular hydrogen and dust grains within the cooler regions of the nebula. These molecules and particles, shielded from the harsh ultraviolet radiation by the surrounding ionized gas, preserve some of the original stellar material in forms that can be studied to understand the chemical composition of the progenitor star. Polarization studies of the nebula's light reveal the presence of magnetic fields threading through the structure. These fields, originally generated within the dying star, become frozen into the expanding gas and help shape the nebula's morphology. The interaction between the magnetic field and the stellar wind creates preferred directions for material flow, contributing to the complex braided patterns visible in high-resolution images. The fate of the Helix Nebula is written in the physics of its expansion and the evolution of its central star. Over the next few thousand years, the nebula will continue to expand and fade as the gas disperses into the surrounding interstellar medium. The central white dwarf will gradually cool, reducing the energy available to ionize the surrounding material. Eventually, the glowing eye will fade to invisibility, leaving only the white dwarf as a testament to the star that once illuminated this corner of the galaxy. From a hypothetical vantage point within the nebula, an observer would find themselves surrounded by a cathedral of glowing gas, with wispy filaments stretching in all directions like cosmic aurora. the central white dwarf would appear as an intensely bright blue-white star, far more luminous than any star visible from Earth. The nebular gas would glow softly in all directions, creating an environment where night and day lose their meaning in the perpetual twilight of ionized hydrogen and oxygen. The Helix Nebula serves as a preview of our own sun's distant future. In approximately 5 billion years, our star will undergo a similar transformation, swelling into a red giant before ejecting its outer layers to form a planetary nebula. The Earth, if it survives the sun's red giant phase, would find itself embedded within a glowing shell of gas, experiencing conditions similar to those within the Helix Nebula today. The enduring appeal of the Helix Nebula lies not only in its striking resemblance to a cosmic eye, but also in what it represents: the transformation of stellar death into cosmic beauty. It reminds us that even the end of a star's life can create something magnificent, a glowing beacon that enriches the interstellar medium and provides the raw materials for future generations of stars and planets. In gazing upon this celestial eye, we witness both an ending and a beginning, a star's final gift to the universe wrapped in layers of luminous gas that will glow for millennia to come. The Eridanus Supervoid. Deep within the constellation, Eridanus lies one of the most mysterious and empty regions of our observable universe. The Eridanus Supervoid, also known as the CMB cold spot, represents a cosmic anomaly so vast and barren that it challenges our understanding of how the universe should be structured. This immense region of space, nearly devoid of galaxies and stretching across 1 billion light-years, exists as a cosmic desert that seems to contradict the expected distribution of matter throughout the cosmos. The discovery of the Eridanus Supervoid emerged from observations of the cosmic microwave background radiation, the afterglow of the Big Bang that permeates all of space. When astronomers mapped this ancient light with unprecedented precision, they found an unusually cold spot in the constellation Eridanus, a region where the temperature of the background radiation was significantly lower than the surrounding areas. This temperature difference, though measuring only a few millionths of a degree, represents one of the largest temperature anomalies ever detected in the cosmic microwave background. The connection between this cold spot and the supervoid became apparent through extensive galaxy surveys that revealed an extraordinary absence of matter in the same region of sky. Where astronomers would typically expect to find thousands of galaxies distributed throughout space, they instead discovered a cosmic wasteland containing far fewer galaxies than statistical models predict. This correlation between the cold spot in the ancient light and the current void in galaxy distribution suggests a profound connection between the early universe and the large-scale structure we observe today. The scale of the Eridanus Supervoid defies easy comprehension. Spanning approximately 1 billion light-years across, it represents one of the largest known structures in the universe, yet it is defined entirely by what it lacks rather than what it contains. To traverse this cosmic emptiness at the speed of light would require a journey lasting longer than the current age of the universe, highlighting the immense scales involved in cosmic structure formation. The formation of such an enormous void presents significant challenges to our standard models of cosmic evolution. Computer simulations of universe development, based on our current understanding of dark matter and dark energy, struggle to produce voids of this magnitude within the time frame since the Big Bang. The existence of the Eridanus Supervoid suggests that either our models are incomplete or that rare, extreme fluctuations in the early universe's density field were more common than previously thought. Temperature measurements within and around the supervoid reveal subtle but important variations that provide clues about its nature and origin. The integrated Sachs-Wolf effect, which occurs when photons from the cosmic microwave background pass through regions of changing gravitational potential, appears to be responsible for the observed cooling. As photons travel through the expanding void, they lose energy climbing out of the gradually weakening gravitational field, arriving at our telescopes with slightly less energy and thus appearing cooler. The few galaxies that do exist within the Eridanus Supervoid display characteristics that set them apart from galaxies in more typical cosmic environments. These isolated island universes often show signs of slower evolution, with less efficient star formation and different morphological properties compared to galaxies in denser regions. The The lack of neighboring galaxies means these systems have experienced fewer gravitational interactions and mergers, preserving some characteristics from their early formation that have been erased elsewhere through cosmic time. The boundaries of the supervoid are not sharp edges, but gradual transitions where the galaxy density slowly increases from nearly zero to more typical cosmic values. These transition zones, spanning tens of millions of light years, represent regions where the void's influence begins to give way to the gravitational attraction of surrounding matter concentrations. The study of these boundary regions provides insights into how cosmic voids interact with the larger cosmic web of matter. Dark matter plays a crucial role in understanding the Eridanus Supervoid's structure and evolution. While ordinary matter galaxies are largely absent from the region, dark matter likely still threads through the void in sparse filaments and sheets, providing the gravitational scaffolding that connects this empty region to the broader cosmic web. The distribution of this invisible matter determines how the void will evolve over cosmic time and influences the motion of surrounding galaxy clusters. The supervoid's effect on the cosmic microwave background extends beyond simple temperature variations. Detailed analysis reveals subtle patterns in the polarization of the ancient light that passes through the region, providing additional information about the void's density profile and magnetic field structure. These polarization measurements help astronomers distinguish between different theoretical models for the void's formation and evolution. Recent studies have suggested that the Eridanus Supervoid might not be a single, coherent structure, but rather a series of smaller voids aligned along our line of sight. This possibility, known as the multiple void hypothesis, could explain the extreme temperature anomaly without requiring such an improbably large single void. However, galaxy surveys have not yet definitively resolved whether we are observing one enormous void or several smaller ones that happen to align in our direction. The existence of the supervoid has implications for our understanding of cosmic inflation, the rapid expansion period that occurred in the universe's first fraction of a second. The size and characteristics of the void provide constraints on the nature of the quantum fluctuations that seeded all cosmic structure. If the void formed from a single, extremely rare fluctuation in the early universe, it might represent evidence for specific types of inflationary models or exotic physics operating during the universe's birth. The long-term fate of the Eridanus Supervoid depends on the balance between cosmic expansion and gravitational collapse. Dark energy, the mysterious force driving the universe's accelerating expansion, ensures that most of the void will continue to expand and become even emptier over time. However, the densest regions within the void might eventually collapse to form new galaxies and structures, though this process would take many billions of years to complete. From a hypothetical observer positioned within the Eridanus Supervoid, the night sky would present a profoundly different appearance than the star-filled heavens we know on Earth. The nearest galaxies would be hundreds of millions of light years away, appearing as faint smudges barely visible even with powerful telescopes. The cosmic microwave background radiation would be the dominant source of illumination, creating a universe where the afterglow of creation provides more light than all the galaxies combined. The study of supervoids like Eridanus has revealed that the universe's large-scale structure resembles a cosmic web, with matter concentrated along filaments and sheets that surround vast empty regions. These voids occupy the majority of the universe's volume, even though they contain only a tiny fraction of its matter. Understanding how these enormous empty spaces formed and evolved provides crucial insights into the fundamental forces and processes that have shaped our cosmos. The Eridanus Supervoid challenges us to reconsider our assumptions about cosmic homogeneity and the uniformity of the universe on large scales. While the cosmos appears remarkably uniform when averaged over extremely large volumes, the existence of such enormous voids demonstrates that significant variations in matter density can persist across scales approaching the size of the observable universe itself. As our observational techniques continue to improve, the Eridanus Supervoid will undoubtedly reveal more of its secrets. Future surveys will map its boundaries with greater precision, determine whether it represents a single structure or multiple aligned voids, and provide better constraints on the theoretical models that attempt to explain its existence. This cosmic emptiness serves as a natural laboratory for testing our understanding of gravity, dark matter, dark energy, and the fundamental processes that govern the universe's evolution on the largest possible scales. On the edge of the observable universe, journey with us to the ultimate frontier of human knowledge, a boundary defined not by space but by time itself. At the edge of the observable universe, approximately 46.5 billion light-years from Earth, we encounter a realm where cosmic history meets the limits of physics, where time appears to slow to a crawl, and where the very concepts of here and there begin to lose their meaning. This is not a physical edge in any conventional sense, but rather the horizon of all that we can ever hope to observe or understand about our cosmos. The edge of the observable universe represents the farthest distance from which light has had time to reach us since the Big Bang occurred 13.8 billion years ago. However, due to the expansion of space itself, this boundary lies much farther away than 13.8 billion light-years. As light traveled toward us over cosmic time, the space through which it moved was simultaneously expanding, stretching the distance between its origin point and our location. This cosmic expansion has carried the sources of the most ancient light we can observe to their current distance of nearly 47 billion light-years away. At this cosmic frontier, we observe not distant galaxies or stars, but the cosmic microwave background radiation itself, the afterglow of the Big Bang Bang when the universe first became transparent to light. This ancient illumination, emitted when the cosmos was only 380,000 years old, represents the oldest light in the universe and the most distant phenomenon we can directly observe. Beyond this boundary lies the cosmic dark age, a period before stars and galaxies formed, when the universe was filled with neutral hydrogen and remained opaque to electromagnetic radiation. The peculiar nature of time at the edge of the observable universe creates one of cosmology's most fascinating paradoxes. Due to the finite speed of light and the vast distances involved, we observe this boundary as it existed in the distant past, when the universe was 1,000 times smaller and 1,000 times hotter than it is today. The cosmic microwave background shows us the universe at a temperature of about 3,000 Kelvin, when electrons and protons first combined to form neutral atoms, allowing light to travel freely through space for the first time. The expansion of the universe introduces additional complexity to our understanding of this cosmic edge. Space itself is expanding at every point, carrying distant objects away from us at velocities that increase with distance. At the edge of the observable universe, this recession velocity approaches the speed of light itself, creating a cosmic horizon beyond which objects recede so rapidly that their light can never reach us, no matter how long we wait. The cosmic microwave background radiation that defines this boundary exhibits remarkable uniformity, with temperature variations of only a few parts in 100,000. This near-perfect smoothness across the entire sky presents a puzzle known as the horizon problem. Regions of the cosmic microwave background that appear on opposite sides of the sky were never in causal contact with each other, yet they display nearly identical temperatures. This observation provides strong evidence for cosmic inflation, a period of exponential expansion in the universe's first fraction of a second that stretched tiny, causally connected regions to cosmic scales. The slight temperature fluctuations that do exist in the cosmic microwave background represent the seeds of all future cosmic structure. These minute density variations, imprinted when the universe was a smooth, nearly uniform plasma, would eventually grow under the influence of gravity to become the galaxies, stars, and planets we observe today. In studying the cosmic microwave background, we observe not only the universe's distant past, but also the blueprint for its entire future evolution. The polarization patterns within the cosmic microwave background provide additional information about conditions at the edge of the observable universe. These subtle alignments in the ancient light's electric field vector preserve information about the density and velocity variations in the primordial plasma, offering insights into the physics of the early universe that cannot be obtained through temperature measurements alone. Recent detections of specific polarization patterns have provided evidence for gravitational waves generated during cosmic inflation, opening new windows into the universe's first moments. Beyond the cosmic microwave background, lies a region we can never directly observe with electromagnetic radiation, but whose existence we can infer through other means. Gravitational waves, ripples in space-time itself, can potentially carry information from epochs even earlier than the cosmic microwave background, including the inflationary period and possibly the moment of the Big Bang itself. These gravitational signatures represent our only hope of observing beyond the traditional edge of the observable universe. The expansion rate of the universe at this cosmic boundary reveals fundamental information about the nature of dark energy, the mysterious force driving cosmic acceleration. Measurements of the cosmic microwave background's temperature and polarization patterns provide precise constraints on cosmological parameters, including the rate of expansion, the density of dark matter, and the properties of dark energy. These observations from the universe's edge help determine the cosmos's ultimate fate and the fundamental constants that govern physical reality. The isotropy of the cosmic microwave background, its remarkable uniformity in all directions, suggests that the universe extends far beyond our observable horizon. The edge we observe represents only the limit of our current observational capabilities, not a true boundary of space itself. The universe likely continues beyond this horizon, possibly infinitely, containing regions that will forever remain beyond our observational reach due to the fundamental limitations imposed by the speed of light and cosmic expansion. Recent observations have revealed subtle anomalies in the cosmic microwave background that challenge our standard model of cosmology. Large-scale asymmetries and unexpected correlations in the temperature patterns suggest that the universe's earliest moments may have been more complex than previously thought. These anomalies might indicate new physics operating at the universe's birth, or suggest that our observable region represents only a small patch of a much larger, more varied cosmos. The concept of cosmic horizons extends beyond the simple observational boundary we can detect today. As the universe continues to expand and age, the observable universe will actually grow larger, allowing us to see light from regions that are currently beyond our reach. However, the accelerating expansion driven by dark energy ensures that many objects we can observe today will eventually disappear beyond a different type of horizon, the event horizon of cosmic expansion, beyond which objects recede faster than light can travel. The edge of the observable universe also represents a boundary in our understanding of causality and information flow. Events occurring beyond this horizon cannot influence our local region of space, creating a natural limit to the size of causally connected regions in the cosmos. This limitation has profound implications for theories that attempt to explain the universe's origin and evolution, suggesting that local physics experiments can only test theories up to certain scales and energies. The temperature of space itself at the edge of the observable universe reflects the cosmic microwave background radiation, currently measured at 2.725 Kelvin above absolute zero. This temperature represents the coolest natural environment in the universe, colder than the interior of molecular clouds and approaching the fundamental limits imposed by quantum mechanics. As the universe continues to expand, this temperature will continue to decrease, approaching absolute zero over cosmic time. From a hypothetical vantage point at the edge of the observable universe, an observer would find themselves in a unique position to witness cosmic history. They would see the universe as it existed billions of years ago, with young galaxies forming their first stars and the cosmic web beginning to take shape. However, due to time dilation effects and the extreme redshift of light at this cosmic boundary, the passage of time itself would appear distorted, with distant events appearing to unfold in slow motion. The study of the observable universe's edge continues to yield new insights into fundamental physics and cosmology. Future observations with increasingly sensitive instruments will provide more detailed maps of the cosmic microwave background, potentially revealing additional information about cosmic inflation, dark matter, and the universe's ultimate origin. These observations from the very edge of knowledge continue to expand our understanding of the cosmos and our place within it, demonstrating that even at the limits of the observable universe, new discoveries await those who dare to look beyond the boundaries of the known. Inside the pillars of creation, deep within the Eagle Nebula, approximately 7,000 light-years from Earth, stand some of the universe's most magnificent stellar nurseries. The pillars of creation, immortalized by the Hubble Space Telescope, rise like cosmic mountains from a sea of glowing gas and dust, serving as both monuments to stellar birth and witnesses to the ongoing process of star formation. These towering structures, each several light years tall, represent active stellar factories where the fundamental forces of gravity, radiation, and turbulence collaborate to transform diffuse cosmic material into the brilliant stars that illuminate our galaxy. The pillars of creation formed within the Eagle Nebula through a complex interplay of stellar winds, radiation pressure, and gravitational collapse. The massive hot young stars that illuminate the surrounding nebula emit intense ultraviolet radiation that ionizes the nearby gas, creating the characteristic red glow of hydrogen emission. This same radiation exerts pressure on the surrounding material, sculpting the dense molecular clouds into the distinctive pillar shapes we observe today. The pillars themselves represent regions of higher density that have resisted erosion by the stellar winds, standing as cosmic monuments against the destructive forces of their stellar neighbors. Within these towering columns of gas and dust, conditions are remarkably different from the empty space between stars. The density of material, while still incredibly sparse by terrestrial standards, is millions of times greater than typical interstellar space. Temperatures within the pillars hover around 10 to 20 Kelvin, just barely above absolute zero, creating an environment cold enough to freeze virtually any known substance. In this frigid darkness, molecules can survive, and complex chemistry can occur, setting the stage for the gravitational collapse that will eventually give birth to new stars. The chemistry within the pillars of creation reveals a rich tapestry of molecular species that serve as both the building blocks and tracers of star formation. Water, ammonia, carbon monoxide, and hundreds of other molecules exist in these cosmic clouds, many of them organic compounds that would be familiar to terrestrial chemists. These molecules form on the surfaces of microscopic dust grains, tiny particles of silicate and carbon that serve as cosmic laboratories for chemical reactions that would be impossible in the emptiness of space. The process of star formation within the pillars begins with gravitational instabilities in the dense molecular gas. When a region of the cloud becomes sufficiently dense, its own gravity begins to dominate over the thermal pressure of the gas, leading to gravitational collapse. This collapse accelerates as the material becomes denser, heating up through gravitational compression until nuclear fusion ignites in the core, marking the birth of a new star. The entire process, from initial collapse to stellar ignition, typically takes several million years for stars similar to our Sun. The tips of the pillars of creation, known as elephant trunk structures, represent some of the most active regions of current star formation. These dense knots of material, compressed by the surrounding radiation pressure, contain enough mass to form multiple star systems. Observations have revealed the presence of young stellar objects embedded within these regions, protostars that are still gathering material from their surrounding cocoons. These nascent stars remain hidden from optical telescopes by the dense dust that surrounds them, but their presence is revealed through infrared observations that can penetrate the obscuring material. The violent environment within an active star-forming region creates a complex ecosystem of physical processes. Stellar winds from newly formed massive stars create shock waves that propagate through the surrounding medium, compressing some regions while dispersing others. These shocks can both trigger new episodes of star formation by compressing nearby gas clouds and terminate star formation by dispersing the raw material needed for stellar birth. The result is a dynamic, ever-changing landscape where creation and destruction occur simultaneously. The magnetic fields threading through the pillars of creation play a crucial role in regulating the star formation process. These fields, typically aligned with the pillar structures themselves, provide support against gravitational collapse and help channel the flow of material during the early stages of stellar formation. The interaction between magnetic fields, turbulence, and gravity creates a complex three-dimensional dance that determines where and when new stars will form within the pillars. Observations across different wavelengths of light reveal the multi-layered structure of the pillars of creation. In visible light, we see the ionized gas glowing in characteristic emission lines, creating the familiar red and orange hues of hydrogen and sulfur. infrared observations penetrate deeper into the structures, revealing the warm dust heated by embedded protostars and the complex filamentary networks that transport material throughout the pillars. Radio observations detect the coldest, densest regions where molecules emit characteristic spectral signatures, mapping the raw material available for future star formation. The discovery of jets and outflows from protostars within the pillars has revealed another layer of complexity in the star formation process. These high-velocity streams of material, launched by the magnetic fields and accretion processes around young stars, can extend for light years beyond their stellar sources. The jets interact with the surrounding molecular material, creating shock waves that heat and ionize the gas, contributing to the overall energy budget of the star-forming region. The dust within the pillars of creation serves multiple functions in the star formation process. These microscopic particles, composed primarily of silicates and carbon compounds, provide surfaces for molecular formation and help cool the gas by radiating away thermal energy. The dust also plays a crucial role in shielding the interior of molecular clouds from the destructive ultraviolet radiation of nearby stars, maintaining the cold, dense conditions necessary for gravitational collapse to occur. Recent studies have suggested that the pillars of creation may have already been destroyed by a supernova explosion that occurred approximately 6,000 years ago. However, due to the finite speed of light and the 7,000 light-year distance to the Eagle Nebula, this destruction would not be visible from Earth for another 1,000 years. This possibility highlights the dynamic nature of star-forming regions and reminds us that the cosmic landscapes we observe represent moments frozen in time by the limitations of light travel. The study of embedded young stellar objects within the pillars has provided crucial insights into the early stages of stellar evolution. These protostars, still surrounded by their birth material, exhibit characteristics that bridge the gap between molecular clouds and main sequence stars. Their spectral signatures reveal the presence of accretion disks, the flattened structures of material that spiral into the growing protostar and may eventually form planetary systems. From a hypothetical vantage point within the pillars of creation, an observer would find themselves in a landscape of ethereal beauty and cosmic violence. The surrounding gas would glow faintly in the light of distant stars, while embedded protostars would appear as brilliant beacons, surrounded by swirling disks of material. The environment would be filled with the subtle dynamics of gravitational collapse, magnetic field interactions, and the constant interplay between creation and destruction that characterizes active star-forming regions. The pillars of creation represent more than just a spectacular astronomical photograph. They embody the fundamental processes that have shaped our galaxy and continue to create the stars that illuminate the cosmos. Within these towering structures, we witness the transformation of the most basic ingredients of the universe into the complex stellar systems that make galaxies shine, reminding us that star formation is a violent, dynamic phenomenon that shapes the structure and evolution of the universe on the largest scales. A Magnetar's surface. Imagine standing on a surface where the magnetic field is so intense that it could distort the very atoms in your body, stretching them into needle-like shapes before tearing them apart entirely. Welcome to the surface of a magnetar, the most magnetically powerful object in the known universe. These extraordinary neutron stars possess magnetic fields trillions of times stronger than Earth's, creating an environment so extreme that the fundamental laws of physics operate in ways that challenge our understanding of matter and energy. Magnetars represent the most extreme members of the neutron star family, stellar remnants left behind when massive stars exhaust their nuclear fuel and collapse catastrophically. What distinguishes magnetars from ordinary neutron stars is their extraordinary magnetic field strength, which can reach up to a quadrillion times more powerful than Earth's magnetic field. To put this in perspective, a magnetar's magnetic field at a distance of 1,000 kilometers would be strong enough to strip the magnetic information from every credit card on Earth. The surface of a magnetar exists in a state of constant tension and instability due to the immense magnetic forces at play. The magnetic field lines threading through the neutron star's crust create enormous stresses in the crystalline structure of the surface material. These stresses can become so intense that they overcome the incredible structural strength of neutron-degenerate matter, causing the surface to crack and shift in events known as starquakes. When these magnetic earthquakes occur, they release more energy in a fraction of a second than our sun produces in an entire year. The magnetic field configuration on a Magnetar's surface creates a landscape unlike anything found elsewhere in the universe. The field lines emerge from the stellar interior and loop through the surrounding space, creating invisible highways along which charged particles are forced to travel. These magnetic field lines can become twisted and tangled by the star's rotation and internal dynamics, building up enormous amounts of magnetic energy that can be released explosively when the field lines reconnect. The temperature distribution across a Magnetar's surface reflects the complex interplay between magnetic heating and radiative cooling. While ordinary neutron stars cool steadily over millions of years, Magnetars maintain surface temperatures of 10 million Kelvin or more through magnetic heating processes. The decay and reconnection of magnetic field lines inject energy into the surface layers, keeping these ancient stellar remnants hot and active long after their formation. The atmosphere of a magnetar consists of a thin layer of highly magnetized plasma that behaves according to principles rarely encountered elsewhere in astrophysics. In such extreme magnetic fields, the motion of electrons and ions becomes highly constrained, forcing them to move primarily along the magnetic field lines. This creates an atmosphere with dramatically different properties in directions parallel and perpendicular to the magnetic field, resulting in highly anisotropic thermal and optical characteristics. The quantum mechanical effects that govern matter in such intense magnetic fields produce phenomena that exist nowhere else in nature. Atoms in a magnetar's magnetic field become elongated into cylindrical shapes, with their electron orbitals compressed into narrow strips aligned with the field direction. The energy levels of atoms shift dramatically, altering their spectroscopic signatures and creating new quantum states that cannot be reproduced in terrestrial laboratories. The surface composition of a magnetar reflects both its neutron star heritage and the unique effects of extreme magnetization. The outermost layers consist primarily of iron and other heavy elements arranged in a crystalline lattice structure, but the presence of the intense magnetic field modifies this structure in profound ways. The magnetic pressure becomes comparable to, or even exceeds the material pressure, creating conditions where the magnetic field directly influences the arrangement of atomic nuclei. Magnetar surfaces exhibit periodic variations in brightness and spectral properties due to their rotation, which typically occurs with periods ranging from a few seconds to several minutes. As the magnetar spins, different regions of its surface come into view, each with potentially different magnetic field strengths, temperatures, and emission characteristics. These rotational modulations provide astronomers with a way to map the surface properties of these distant objects. The emission of high-energy radiation from magnetar surfaces creates some of the most energetic phenomena observed in astronomy. When magnetic field lines reconnect, or when the surface cracks under magnetic stress, enormous amounts of energy are released in the form of X-rays and gamma rays. These bursts can briefly outshine entire galaxies and have been detected from magnetars located thousands of light years away. The interaction between a magnetar's magnetic field and any surrounding material creates additional complexity in the surface environment. If the magnetar accretes material from a companion star or from the interstellar medium, this material becomes channeled along the magnetic field lines toward the magnetic poles. As the material approaches the surface, it becomes compressed and heated to temperatures of hundreds of millions of degrees, creating hotspots that can outshine the rest of the stellar surface. The magnetic field extends far beyond the stellar surface, creating a magnetosphere that influences matter and radiation across distances of thousands of kilometers. This magnetosphere traps charged particles and forces them to move in complex helical paths around the magnetic field lines. The interaction between these trapped particles and the magnetic field generates radio waves and other forms of electromagnetic radiation that can be detected by radio telescopes. Recent observations have revealed that some magnetars undergo sudden changes in their rotational periods, suggesting that their magnetic fields are constantly evolving and reorganizing. These timing glitches may result from internal changes in the magnetic field configuration that affect the star's moment of inertia or from sudden releases of magnetic energy that alter the surface structure. The formation mechanism for magnetic fields remains one of the outstanding puzzles in stellar astrophysics. Current theories suggest that these extreme fields may be generated during the core collapse process that creates the neutron star, possibly through the rapid rotation of the collapsing stellar core, or through dynamo processes operating in the newly formed neutron star. The surface gravity on a magnetar is approximately 100 billion times stronger than Earth's gravity, but the presence of the extreme magnetic field adds additional forces that can dominate over gravitational effects in certain regions. Near the magnetic poles, the magnetic pressure can exceed the gravitational pressure, creating conditions where the magnetic field directly supports the weight of surface material. From a theoretical perspective, standing on a magnetar's surface would subject an observer to forces and conditions that would fundamentally alter the nature of matter and energy. The intense magnetic field would not only distort any atoms present, but would also affect the propagation of light, the behavior of elementary particles, and even the structure of the quantum vacuum itself. The surface would represent a natural laboratory for testing our understanding of physics under the most extreme conditions possible. The study of magnetar surfaces continues to provide crucial insights into the behavior of matter under extreme conditions, and the role of magnetic fields in shaping stellar evolution. These remarkable objects serve as cosmic laboratories where the most fundamental laws of physics operate in regimes that cannot be reproduced on Earth, offering unique opportunities to test our theoretical understanding of magnetism, quantum mechanics, and matter at nuclear densities, orbiting a white dwarf. In the quiet depths of space, far from the bustling activity of stellar nurseries and the violent explosions of supernovae, there exists a class of celestial objects that embodies both the end of one cosmic story and the beginning of another. White dwarfs represent the final chapter in the lives of most stars, including our own sun, yet they continue to shine with a gentle, persistent light that can last for billions of years. Imagine drifting through space toward one of these remarkable objects. From a distance, a white dwarf appears as a small, brilliant point of light, often with a subtle blue-white tint that speaks to its incredible surface temperature. As we draw closer, the true nature of this stellar remnant becomes apparent. What we are approaching is not merely a star in the traditional sense, but rather the exposed core of what was once a much larger, more luminous star. The journey to understanding white dwarfs begins with comprehending their extraordinary density. These objects pack roughly the mass of our Sun into a sphere about the size of Earth. To put this in perspective, a teaspoon of white dwarf material would weigh approximately as much as an elephant. This incredible compression occurs when a star exhausts its nuclear fuel and can no longer support itself against its own gravitational pull. The outer layers are expelled into space, creating beautiful planetary nebulae, while the core contracts until the pressure becomes so intense that electrons are squeezed into a degenerate state. In this degenerate matter, electrons occupy every available energy level, up to what physicists call the Fermi energy. This creates a unique form of pressure that doesn't depend on temperature, but rather on the density of electrons themselves. It's this electron degeneracy pressure that prevents the white dwarf from collapsing further, creating a stable configuration that can persist for eons. The surface of a white dwarf tells a story of intense heat and gradual cooling. When first formed, these stellar corpses can reach surface temperatures of over 100,000 degrees Celsius, making them far hotter than the sun's surface. However, unlike active stars, white dwarfs have no internal energy source to maintain this heat. They shine purely from the thermal energy stored within their dense material, slowly radiating this heat away into the cosmos. This cooling process occurs with remarkable predictability. Over millions and billions of years, a white dwarf gradually fades from brilliant blue-white to yellow, then to red, and eventually to a theoretical black dwarf, though the universe isn't old enough yet for any white dwarf to have completed this journey. The cooling follows well-understood physical laws, making white dwarfs excellent cosmic timepieces that astronomers use to determine the ages of star clusters and even place constraints on the age of the universe itself. The atmosphere of a white dwarf, if we can call the thin layer of gas surrounding its solid surface an atmosphere, is remarkably pure. The intense gravitational field roughly 100,000 times stronger than Earth's gravity, causes heavy elements to sink toward the surface while lighter elements float upward. This gravitational settling creates atmospheres that are often composed almost entirely of hydrogen or helium, with trace amounts of heavier elements that tell stories of the star's past nuclear fusion history. Some white dwarfs display fascinating atmospheric phenomena. Magnetic fields, often millions of times stronger than Earth's magnetic field, can channel material across the surface, creating patterns of hot and cool regions. These temperature variations cause the white dwarf to appear to pulsate as it rotates, a behavior that allows astronomers to study both the magnetic field structure and the rotation period of these compact objects. Orbiting closer to a white dwarf reveals the profound effects of its intense gravitational field. Space and time themselves are noticeably curved in the vicinity of such a dense object. Light rays bend as they pass near the white dwarf, and time runs slightly slower in the stronger gravitational field near its surface. These relativistic effects, while subtle, are measurable and provide important tests of Einstein's theory of general relativity. The immediate environment around a white dwarf is typically serene, a vast contrast to the chaotic regions surrounding young, active stars. There are no solar winds or coronal mass ejections, no flares or spots marking magnetic activity. Instead, there's a profound stillness, broken only by the steady, gentle emission of thermal radiation carrying away the white dwarf's stored heat. Yet this tranquility can be dramatically interrupted if the white dwarf has a companion star. In binary systems, material from a normal star can spiral inward toward the white dwarf, forming an accretion disk that glows with intense heat generated by friction and gravitational compression. This process can lead to periodic explosive events called novae, where accumulated material on the white dwarf's surface undergoes sudden nuclear fusion. The life cycle of material around a white dwarf follows fascinating patterns. Gas that falls onto the surface becomes compressed and heated until it forms a thin layer of degenerate matter. Over time, this layer can grow until conditions become right for a thermonuclear explosion that blasts the accumulated material back into space. The white dwarf itself survives these events largely unchanged, ready to begin the process anew. From our orbital perspective, we can observe how the white dwarf's gravity affects its surroundings. Planets that might have survived the star's evolution into a white dwarf would now orbit much closer to maintain the same amount of received heat. The habitable zone around a white dwarf lies very close to the stellar remnant, creating unique conditions for any hypothetical worlds that might exist there. These compact objects serve as natural laboratories for studying matter under conditions impossible to replicate on Earth. The combination of extreme density, intense gravitational fields, and gradual cooling provides insights into fundamental physics, from the behavior of degenerate matter to the nature of crystallization under extreme pressure. As white dwarfs cool, their interiors eventually solidify into crystalline structures, with carbon and oxygen atoms arranging themselves into ordered lattices. This crystallization process releases latent heat, slightly slowing the cooling rate and extending the white dwarf's luminous lifetime. The study of white dwarf atmospheres reveals intricate details about stellar evolution and planetary system formation. Spectroscopic observations often detect traces of heavy elements like calcium, magnesium, and iron in their atmospheres. Since these elements should have sunk below the surface due to gravitational settling, their presence indicates ongoing accretion of material, likely from disrupted asteroids or comets that once orbited the star during its main sequence lifetime. This process of planetary system archaeology through white dwarf spectroscopy has revolutionized our understanding of what happens to planetary systems when their host stars die. The chemical signatures preserved in white dwarf atmospheres provide a fossil record of the rocky bodies that once populated these systems, offering glimpses into the compositions of extrasolar asteroids and the remnants of ancient worlds. The rotation of white dwarfs adds another layer of complexity to their behavior. Most white dwarfs spin relatively slowly, having shed much of their angular momentum when they expelled their outer layers. However, some rotate rapidly, particularly those that have gained angular momentum from accreting material in binary systems. These fast rotators can complete a full rotation in just minutes, creating measurable variations in their light outputs as different regions of their surface come into view. Temperature variations across a white dwarf's surface create subtle but detectable changes in brightness and color. Magnetic fields can create cooler spots where field lines emerge from the surface, while other regions remain hotter. These temperature differences, combined with the white dwarf's rotation, produce periodic variations that astronomers can measure with extraordinary precision, revealing details about magnetic field structures and surface compositions. White dwarfs represent a form of cosmic patience that spans geological timescales. They will continue to shine long after all the ordinary stars have burned out, serving as the final lighthouses in an increasingly dark universe. Their gentle glow carries forward the legacy of stellar nucleosynthesis, having helped create many of the heavy elements that make rocky planets and life itself possible. In their quiet persistence, white dwarfs embody both ending and continuity, reminding us that even in death, stars continue to illuminate the cosmos with their stored warmth and accumulated wisdom, bearing witness to the grand cycles of stellar birth, life, and transformation that define our universe, the Galactic Center. Deep within our Milky Way galaxy, beyond the familiar constellations and the comfortable glow of our local stellar neighborhood, lies a region unlike anywhere else in our cosmic home. The Galactic Center represents the gravitational heart of our galaxy, a place where space itself tells a story of immense forces, ancient processes, and the fundamental architecture that holds our entire stellar system together. Located approximately 26,000 light-years from Earth in the direction of the constellation Sagittarius, this central region remains largely hidden from our direct view. Vast clouds of interstellar dust scatter and absorb visible light, creating what astronomers call the zone of avoidance. Yet this cosmic veil only adds to the mystery and wonder of what lies beneath, revealing itself through longer wavelengths of light that can penetrate the dusty shroud. The heart of our galaxy beats with the rhythm of countless stars, moving in complex orbital patterns around an invisible gravitational anchor. This anchor, we now know, is Sagittarius A star, a supermassive black hole containing the mass of over 4 million suns, compressed into a region smaller than our solar system. Its presence shapes everything within thousands of light years, creating a gravitational landscape that governs the motion of gas, dust, and stars throughout the central regions. Surrounding this central black hole, space becomes increasingly crowded with stellar inhabitants. The density of stars near the Galactic Center reaches extraordinary levels, with millions of stars packed into regions that would normally contain just a few dozen. These stars follow elliptical orbits that carry them swooping close to the central black hole before sending them racing back out into the relative emptiness of space. Some of these orbital periods take just 16 years to complete, providing astronomers with the opportunity to watch entire stellar orbits unfold within human lifetimes. The stellar population of the Galactic Center tells a fascinating story of cosmic evolution. Ancient red giants mingle with massive blue supergiants, while populations of older stars speak to billions of years of stellar formation and evolution. These stars have witnessed the galaxy's growth from its earliest epochs, serving as archaeological records of cosmic history. Their chemical compositions reveal the gradual enrichment of the interstellar medium through successive generations of stellar nucleosynthesis. Between these stars, the space of the central region fills with thin but extensive clouds of gas and dust. These materials form intricate structures shaped by magnetic fields, stellar winds, and the tidal forces created by the central black hole. Some regions glow with the warm light of star formation, where new stellar systems continue to emerge despite the challenging environment. Other areas remain dark and cold, reservoirs of material waiting for the right conditions to ignite the nuclear fires of stellar birth. The magnetic environment near the Galactic Center creates some of the most complex field structures known in astronomy. These magnetic fields, thousands of times stronger than those found in our local galactic neighborhood, channel the flow of charged particles and shape the distribution of gas throughout the region. They create vast loops and filaments that stretch across hundreds of light years, forming a three-dimensional web of magnetic architecture that influences everything from star formation to the motion of cosmic rays. Radiation permeates this central region in forms both visible and invisible. High-energy particles accelerated by magnetic fields, and gravitational interactions create a constant background of cosmic rays. X-rays emerge from gas heated to millions of degrees as it falls toward the central black hole or collides with magnetic field structures. Radio waves propagate through the dusty medium, carrying information about the motion and temperature of gas clouds across vast distances. The gravitational dynamics of the Galactic Center create a natural laboratory for studying physics under extreme conditions. Time dilation effects become measurable as objects approach the central black hole, with clocks running noticeably slower in the intense gravitational field. Space itself curves dramatically, bending the paths of light rays and creating gravitational lensing effects that can magnify and distort the appearance of background objects. Within this environment, stellar collisions become far more common than in the galactic disk where we reside. The high stellar density means that stars occasionally pass close enough to each other to exchange material or even merge completely. These interactions can rejuvenate aging stars, create exotic stellar types, or trigger explosive events that briefly outshine entire star clusters. The central parsec, the innermost region within about 3 light-years of the black hole, represents an even more extreme environment. Here, the gravitational field becomes so intense that normal stellar evolution processes are disrupted. Stars can be torn apart by tidal forces, their material forming temporary accretion streams that spiral inward toward the event horizon. Other stars survive these close encounters, but emerge fundamentally altered, stripped of outer layers, or spun up to rapid rotation rates. Gas dynamics in the Galactic Center follow complex patterns influenced by the rotation of the galaxy, magnetic field structures, and the gravitational pull of the central black hole. Material spirals inward through a series of nested structures, from the large-scale bar of our galaxy down to smaller circumnuclear disks, and eventually to the immediate vicinity of the black hole itself. Each scale of motion contributes to the overall flow of material and energy through the system. The observational study of the Galactic Center requires sophisticated techniques to peer through the intervening dust and gas. Infrared observations reveal the motions of individual stars, allowing astronomers to map the gravitational field and confirm the presence of the central black hole. Radio telescopes detect the synchrotron radiation from high-energy particles, while X-ray observations show the hot gas and high-energy processes occurring throughout the region. Despite the seemingly hostile environment, the Galactic Center continues to nurture new generations of stars. Star formation proceeds in the dense molecular clouds that populate the central regions, though the process differs significantly from the more sedate star formation occurring in our local galactic neighborhood. The intense radiation field, strong magnetic fields, and tidal forces all influence how and where new stars can form. The Galactic Center serves as our galaxy's engine room, where fundamental processes of energy generation, matter circulation, and gravitational organization play out on the grandest scales. It represents both the destination toward which all galactic material ultimately flows and the source from which energy and processed matter return to enrich the broader galactic ecosystem. In its complex interplay of matter, energy, and gravity, the Galactic Center embodies the dynamic nature of our cosmic home, reminding us that even in the apparent stillness of space, powerful forces continuously shape and reshape the universe around us. A binary star system. In the vast expanse of our galaxy, where single stars like our Sun might seem to be the norm, a different kind of stellar arrangement actually dominates the cosmic landscape. Binary star systems, where 2 stars orbit around their common center of mass, represent one of the most elegant and fundamental configurations in the universe. These paired stellar companions perform an endless celestial waltz, their gravitational embrace creating some of the most stable and long-lasting partnerships known to astronomy. The gravitational dance between 2 stars follows the same physical principles that govern all orbital motion. Yet the complexity emerges from having 2 massive objects influencing each other simultaneously. Unlike planets orbiting a much more massive star, binary stars often possess comparable masses, creating a more balanced gravitational relationship. where both stars noticeably affect the other's motion. Their orbits trace out elliptical paths around an invisible point called the Great Center, which lies somewhere between the two stars, depending on their relative masses. When two stars of similar mass orbit each other, the barycenter sits roughly halfway between them, causing both stars to execute similar orbital paths. However, when one star significantly outmasses its companion, the barycenter shifts closer to the more massive star, sometimes even lying within its outer layers. In such systems, the more massive star appears to wobble slightly while its smaller companion sweeps through a much larger orbital arc. The formation of binary star systems traces back to the earliest stages of stellar birth. Within the cold, dense molecular clouds where stars are born, gravitational instabilities can cause a collapsing region to fragment into multiple condensations. These fragments, each destined to become a star, can retain enough angular momentum from the original cloud's rotation to establish stable orbits around each other. Alternatively, binary systems can form through gravitational capture, where two independently formed stars encounter each other and become gravitationally bound through their mutual attraction. The orbital periods of binary systems span a remarkable range, from pairs that complete their dance in just hours to those requiring thousands of years for a single orbit. Close binary systems, where stars orbit within a few stellar radii of each other, experience intense gravitational interactions that can dramatically alter their evolution. The tidal forces in such tight systems can distort the stars into egg-shaped ellipsoids, with their surfaces bulging toward each other in response to the powerful gravitational pull. Wide binary systems, conversely, maintain separations of hundreds or thousands of astronomical units, allowing each star to evolve largely independently, while still remaining gravitationally bound. These distant companions may take millennia to complete a single orbit, their connection evident only through precise measurements of their common motion through space over extended periods of observation. The masses of the two stars in a binary system determine not only their orbital characteristics, but also their individual evolutionary paths. More massive stars burn through their nuclear fuel more rapidly, evolving faster than their lower mass companions. This difference in evolutionary timescales creates fascinating scenarios where one star may exhaust its nuclear fuel and begin expanding into a red giant, while its companion remains on the main sequence, still steadily fusing hydrogen in its core. Temperature differences between binary companions create beautiful visual contrasts when observed through telescopes. A hot, blue-white star paired with a cooler, orange companion produces a striking color combination that shifts subtly as the stars orbit each other. These color variations, combined with changes in the total brightness of the system, provide astronomers with detailed information about the star's properties and orbital motion. The gravitational influence between binary companions becomes most dramatic when one star begins to transfer material to the other. This process, known as mass transfer, occurs when one star expands beyond its Roche lobe, the gravitational boundary within which material remains bound to that particular star. Gas flowing from the donor star toward its companion often forms an accretion disk, a swirling structure that heats up through friction and gravitational compression, glowing brightly across multiple wavelengths of light. These accretion processes can lead to spectacular astronomical phenomena. When material accumulates on the surface of a white dwarf companion, the increasing pressure and temperature can trigger explosive nuclear fusion events called novae. These eruptions briefly increase the system's brightness by factors of thousands or even millions, creating new stars that appear suddenly in the night sky before gradually fading back to their original luminosity. The orbital mechanics of binary systems provide natural laboratories for testing fundamental physics. The precise timing of eclipses, where one star passes in front of the other from our perspective, allows astronomers to measure stellar properties with extraordinary accuracy. These measurements have confirmed predictions of Einstein's general relativity, including the gradual decay of orbits due to the emission of gravitational waves. Some binary systems undergo dramatic evolutionary phases that completely transform their appearance and behavior. When a massive star in a binary system explodes as a supernova, the sudden loss of mass can either disrupt the binary entirely sending both stars flying apart at high velocities, or leave behind an exotic remnant such as a neutron star or black hole that continues to orbit its surviving companion. The environments around binary stars create unique conditions for any potential planetary systems. Planets in binary systems must navigate complex gravitational fields, with stable orbits possible either very close to one of the stars or much farther out, beyond the influence of the stellar orbital motion. These circumbinary planets would experience fascinating seasonal variations as their host stars dance around each other, creating changing patterns of illumination and warmth throughout their years. The study of binary star systems has revolutionized our understanding of stellar evolution and galactic structure. These systems serve as cosmic laboratories where we can observe the effects of gravitational interactions, mass transfer, and stellar evolution under conditions impossible to replicate in terrestrial experiments. They provide crucial data for testing theoretical models of stellar structure and evolution, helping astronomers understand how stars live, change, and die throughout the billions of years of their existence. The synchronization that often develops in close binary systems represents one of nature's most elegant examples of gravitational harmony. Tidal forces gradually slow the star's rotation until they become tidally locked, always showing the same face to each other, much like how the moon always shows the same side to Earth. This tidal synchronization creates a stable configuration that can persist for billions of years, with the two stars maintaining their gravitational embrace while slowly evolving together. In their eternal dance, binary star systems embody the fundamental principle that gravity creates order from chaos, bringing together massive objects across vast distances and maintaining their partnerships through the eons. These stellar duets remind us that companionship exists even on cosmic scales, where two suns can find each other in the immensity of space and commit to a gravitational bond that may outlast the very galaxies that contain them. The Horsehead Nebula. In the constellation Orion, where brilliant stars mark the shoulders and belt of the mythical hunter, there exists one of the most recognizable and photographed objects in the night sky. The Horsehead Nebula stands as a testament to the sculptural power of cosmic forces, where interstellar dust and gas have been shaped into a silhouette that captures the imagination and speaks to our pattern-seeking minds. This dark nebula represents far more than its striking appearance suggests, serving as a window into the complex processes that govern the birth and death of stars. Located approximately 1,500 light-years from Earth, the Horsehead Nebula exists as a small dark cloud silhouetted against the bright backdrop of the larger emission nebula known as IC434. This dramatic contrast creates the distinctive profile that gives the nebula its name, with the horse's head and mane clearly defined against the glowing hydrogen gas that stretches across this region of Orion. The entire structure spans roughly 3.5 light-years, from the tip of the horse's nose to the back of its mane, making it a relatively small feature in the grand scale of nebular objects. The dark appearance of the Horsehead results from dense concentrations of cosmic dust that absorb and scatter light from background sources. These microscopic particles, composed primarily of carbon compounds and silicates, are so effective at blocking visible light that they create what appears to be a hole in the star-filled sky. However, this darkness is deceptive, as the nebula glows faintly in infrared wavelengths, revealing the presence of embedded stars and the thermal emission from dust grains warmed by nearby stellar radiation. The sculpting of the Horsehead's distinctive shape results from the complex interplay between stellar winds, radiation pressure, and the varying density of the surrounding interstellar medium. The bright star Sigma Orionis, located just outside the field of view in most photographs, provides the intense ultraviolet radiation that ionizes the surrounding hydrogen gas, causing it to glow with the characteristic red emission that forms the nebula's bright background. This same radiation gradually erodes the dark cloud, slowly eating away at its edges and reshaping its contours over astronomical timescales. Within the dark interior of the Horsehead, conditions remain remarkably cold and stable compared to the turbulent environment that surrounds it. Temperatures hover around 10 degrees above absolute zero, creating an environment where molecules can form and survive. These frigid conditions allow for the formation of complex organic compounds, including alcohols, acids, and other carbon-based molecules that serve as the building blocks for more complex chemistry throughout the universe. The density structure within the Horsehead reveals the nebula's three-dimensional architecture. The darkest regions correspond to the densest concentrations of dust and gas, where material has been compressed by external pressures and gravitational forces. These denser regions serve as potential sites for future star formation, though the current environment may not provide the necessary conditions to trigger widespread stellar birth. Instead, the nebula exists in a delicate balance between the disruptive forces of nearby stellar radiation and the cohesive forces of its own gravity. Magnetic fields thread through the Horsehead structure, influencing the alignment of dust grains and affecting the polarization of light that passes through the nebula. These magnetic forces help to channel the flow of material within the cloud and may play important roles in determining which regions become dense enough to eventually collapse and form new stars. The interaction between magnetic fields and the surrounding stellar winds creates complex patterns of compression and rarefaction throughout the nebula's interior. The chemical composition of the Horsehead provides insights into the processes of cosmic recycling that enrich the interstellar medium with heavy elements. Spectroscopic observations reveal the presence of carbon monoxide, formaldehyde, and other molecules that form through reactions occurring on the surfaces of dust grains. These molecules serve as tracers of physical conditions within the nebula and help astronomers understand how material cycles between different phases of the interstellar medium. The evolutionary timeline of the Horsehead spans millions of years, during which external forces gradually reshape and ultimately disperse the nebular material. The ongoing erosion by stellar radiation creates a complex interface between the dark cloud and the surrounding emission region, with material being photoevaporated from the nebula's surface and carried away by stellar winds. This process creates intricate structures along the boundary between light and shadow, where tendrils of gas stretch outward from the main body of the nebula. Temperature gradients within the Horsehead create distinct zones where different physical and chemical processes dominate. The outer edges, exposed to direct stellar radiation, experience heating that drives the formation of various molecular species and influences the dynamics of gas flow. Deeper within the nebula, cooler conditions allow for the preservation of more fragile molecular compounds and create environments where different types of dust grain chemistry can occur. The Horsehead's position within the larger Orion complex places it at the intersection of multiple stellar formation regions and supernova remnants. This location exposes the nebula to a variety of external influences, from the winds of massive young stars to the shock waves from ancient stellar explosions. These environmental factors contribute to the nebula's current structure and will ultimately determine its fate as astronomical forces continue to reshape the region. Observational studies of the Horsehead across different wavelengths of light reveal complementary aspects of its structure and composition. Visible light observations show the dramatic silhouette that made the nebula famous, while infrared images penetrate the dusty veil to reveal embedded objects and thermal emission from warm dust. Radio observations detect the spectral signatures of various molecules, providing information about the nebula's chemistry and physical conditions. The Horsehead serves as a natural laboratory for studying the physics of interstellar dust and gas under conditions that bridge the gap between diffuse interstellar space and dense stellar nurseries. Its accessibility to detailed observation, combined with its relatively simple geometry, makes it an ideal target for testing theoretical models of nebular structure and evolution. These studies contribute to our broader understanding of how matter behaves in the space between stars and how cosmic environments influence the formation of planetary systems. As we contemplate the Horsehead Nebula, we witness a moment in cosmic time when matter exists in a transitional state between stellar death and potential rebirth. The nebula embodies the ongoing cycle of cosmic recycling, where material expelled from dying stars accumulates in space, undergoes complex chemical evolution, and eventually becomes incorporated into new generations of stars and planets. In its graceful silhouette against the glowing backdrop of space, the Horsehead reminds us that even in the apparent emptiness between stars, nature creates structures of remarkable beauty and scientific significance. Floating through intergalactic space, beyond the spiral arms of our Milky Way, past the gravitational embrace of our local group of galaxies, lies a realm that represents the ultimate frontier of cosmic emptiness. Intergalactic space stretches across distances so vast that light itself requires millions of years to traverse them, creating voids where matter exists in its most dispersed and primordial state. Here, in the spaces between galaxies, we encounter an environment that challenges our understanding of emptiness while revealing the fundamental structure of the universe itself. The journey into intergalactic space begins as we leave behind the familiar stellar neighborhoods and venture beyond the outer edges of galactic halos. The transition occurs gradually as the density of stars, gas, and dust slowly diminishes until we find ourselves in a realm where individual atoms might be separated by distances measured in meters rather than the microscopic scales we associate with ordinary matter. This is not the complete vacuum that early astronomers once imagined, but rather a sparse medium that contains the building blocks of cosmic structure. In this vast emptiness, temperatures hover just a few degrees above absolute zero, maintained by the faint afterglow of the Big Bang that still permeates all of space. The cosmic microwave background radiation provides a subtle warmth that prevents the complete cessation of atomic motion, creating a baseline temperature that has been slowly cooling for nearly 14 billion years. This ancient light carries information about the universe's earliest epochs, when matter and energy first began to separate and organize into the large-scale structures we observe today. The matter that does exist in intergalactic space consists primarily of hydrogen and helium, the simplest and most abundant elements forged in the first few minutes after the Big Bang. These atoms drift through space in an almost perfect vacuum, with densities so low that a cubic meter of intergalactic space might contain only a single atom. Yet, even this tenuous distribution of matter plays a crucial role in cosmic evolution, serving as the raw material from which future generations of galaxies and stars will eventually form. Magnetic fields thread through intergalactic space, though they exist at strengths trillions of times weaker than Earth's magnetic field. These fields, generated by ancient galactic processes and primordial fluctuations, create invisible pathways that can influence the motion of charged particles across cosmic distances. The interaction between these magnetic fields and the sparse plasma of intergalactic space creates phenomena that operate on scales incomprehensible to human experience, with magnetic field lines stretching across hundreds of millions of light years. Dark matter, the mysterious substance that comprises most of the universe's mass, reveals its presence most clearly in intergalactic space. Here, freed from the confusion of ordinary matter interactions, dark matter forms vast networks of invisible scaffolding upon which the cosmic web is constructed. These dark matter filaments guide the flow of ordinary matter through space, creating highways along which galaxies travel and channels through which intergalactic gas can stream toward regions of active star formation. The cosmic web itself represents one of the most remarkable discoveries in modern astronomy, revealing that intergalactic space is not uniformly empty, but organized into an intricate network of filaments, walls, and voids. This web-like structure emerged from tiny quantum fluctuations in the early universe that were amplified by cosmic expansion and gravitational attraction. Today, galaxies exist primarily along the densest portions of these filaments, while vast cosmic voids, some hundreds of millions of light years across, contain almost no visible matter at all. Within these cosmic voids, space approaches its closest approximation to true emptiness. Here, the expansion of the universe proceeds almost unimpeded by gravitational forces, allowing regions of space to grow larger and more empty over time. The few atoms that do exist in these voids experience almost no interactions with their neighbors, creating conditions that approach the theoretical limits of isolation and emptiness that physics allows. The expansion of space itself becomes most apparent in intergalactic regions, where the Hubble flow carries distant objects away from each other at velocities that increase with distance. This expansion does not represent motion through space, but rather the stretching of space itself, a phenomenon that can only be properly understood through Einstein's theory of general relativity. In intergalactic space, we witness the universe growing larger, creating new volumes of emptiness while gradually diluting the density of matter and energy. Gravitational waves propagate freely through intergalactic space, carrying information about cataclysmic events that occurred billions of years ago in distant galaxies. These ripples in space-time itself travel at the speed of light, unimpeded by the sparse matter they encounter along their journey. When they finally reach our detectors on Earth, they carry pristine information about black hole mergers, neutron star collisions, and other extreme phenomena that shape the universe's evolution. The chemistry of intergalactic space remains remarkably simple, consisting almost entirely of the lightest elements produced in the first few minutes after the Big Bang. Unlike the complex chemistry found within galaxies, where successive generations of stellar nucleosynthesis have produced dozens of heavier elements, intergalactic space preserves a record of primordial conditions. This chemical simplicity provides astronomers with windows into the universe's earliest epochs, when the fundamental ratios of hydrogen to helium were first established. Cosmic rays, high-energy particles, accelerated by magnetic fields and shock waves, travel through intergalactic space for millions of years before eventually interacting with matter. These particles, which can possess energies far exceeding anything achievable in terrestrial particle accelerators, use intergalactic space as a vast laboratory where they undergo interactions impossible to study under earthly conditions. Their journeys connect distant regions of the universe, carrying energy and information across cosmic distances. The temperature structure of intergalactic space reflects the complex history of cosmic evolution. While most regions remain cold, having been warmed only by the cosmic microwave background, some areas show evidence of heating by energetic processes. Supernova explosions, active galactic nuclei, and the formation of galaxy clusters can inject energy into intergalactic space, creating temperature variations that persist for billions of years and influence the subsequent evolution of cosmic structure. Light from the most distant galaxies travels through intergalactic space for billions of years before reaching our telescopes, carrying information about the universe as it existed when the first stars and galaxies were forming. This light encounters the sparse hydrogen gas that fills intergalactic space, creating absorption features that allow astronomers to study the properties and evolution of this tenuous medium across cosmic time. These observations reveal how intergalactic space has changed as the universe has aged and evolved. The future evolution of intergalactic space depends on the ultimate fate of cosmic expansion. Current observations suggest that the expansion will continue indefinitely, driven by the mysterious dark energy that appears to permeate all of space. If this continues, intergalactic regions will become increasingly empty and cold, eventually reaching temperatures and densities that approach absolute limits. In this far future, intergalactic space will become the dominant environment in a universe where galaxies exist as isolated islands of matter in an ever-expanding ocean of emptiness. In contemplating intergalactic space, we encounter both the largest and smallest scales of cosmic structure. Here, the quantum fluctuations that seeded galaxy formation reveal their macroscopic consequences, while the fundamental forces of nature operate across distances that challenge our ability to comprehend scale and time. This realm of cosmic emptiness reminds us that even nothingness has structure and history, and that the spaces between objects often contain as much scientific interest as the objects themselves. Near a wormhole, in the deepest mathematics of Einstein's general relativity, lies a solution so extraordinary that it challenges our fundamental understanding of space and time. The wormhole, or Einstein-Rosen bridge, represents a theoretical passage through space-time that could connect distant regions of our universe, or even link entirely separate universes. Though no wormhole has ever been observed, their mathematical possibility emerges naturally from the equations that govern gravity, inviting us to explore one of the most fascinating concepts in theoretical physics. The approach to a wormhole would reveal itself gradually through the subtle distortion of light and space around its entrance. Unlike the event horizon of a black hole, which marks a point of no return, a wormhole's throat represents a passage rather than a destination. The geometry of space-time near a wormhole creates a region where the familiar rules of distance and direction acquire new meaning, as the shortest path between 2 points might curve through dimensions beyond our ordinary three-dimensional perception. The mathematical structure of a wormhole emerges from solutions to Einstein's field equations that describe how matter and energy curve space-time. These solutions reveal geometries where space can be folded and connected in ways that create shortcuts through the fabric of reality itself. The simplest models describe a tunnel-like structure with two mouths connected by a throat, where the distance through the wormhole could be far shorter than the distance around it through normal space. Near the entrance to a wormhole, the curvature of space-time would create remarkable optical effects. Light rays following the curved geometry would appear to bend and focus in unexpected ways, potentially creating multiple images of distant objects or revealing views of regions that lie on the far side of the passage. The gravitational lensing effect would distort the apparent positions and brightness of background stars, creating a characteristic signature that might allow astronomers to identify such objects if they exist. The tidal forces experienced near a wormhole depend critically on its size and the specific geometry of its construction. For traversable wormholes large enough to permit safe passage, the tidal effects could be surprisingly gentle, allowing matter to pass through without being torn apart by differential gravitational forces. This contrasts sharply with the extreme tidal forces found near black holes, where the difference in gravitational pull between head and feet would quickly become lethal. The stability of a wormhole presents one of the greatest challenges to their physical existence. Most solutions to Einstein's equations that describe wormhole geometries require the presence of exotic matter with negative energy density to keep the throat from collapsing. This hypothetical exotic matter would need to violate the energy conditions that govern ordinary matter, creating regions where the energy density becomes negative relative to the surrounding space-time. Such matter has never been observed in nature, though quantum effects in laboratory settings have produced small amounts of negative energy under carefully controlled conditions. The interior of a wormhole throat would represent a unique environment where the concepts of inside and outside lose their conventional meaning. Travelers passing through would experience a transition between different regions of space-time without ever crossing a physical boundary in the traditional sense. The passage might appear as a tunnel-like structure where the walls consist of curved space-time itself, rather than material substances. Time dilation effects near a wormhole could create fascinating scenarios for travelers making the journey between its mouths. Depending on the specific geometry and the motion of the wormhole mouths relative to each other, the passage through the throat might involve traveling into the past or future relative to the external universe. This possibility raises profound questions about causality and the nature of time that physicists continue to explore through theoretical investigation. The quantum effects that occur near wormhole throats introduce additional complexity to their theoretical properties. Vacuum fluctuations, the spontaneous creation and annihilation of particle pairs that occurs throughout empty space, would be amplified by the extreme curvature near the wormhole entrance. These quantum processes could potentially destabilize the wormhole structure, or create feedback loops that either strengthen or destroy the exotic matter needed to maintain the passage. Different types of wormhole solutions exist within the framework of general relativity, each with distinct properties and requirements. Some models describe traversable wormholes that allow two-way passage, while others represent one-way passages similar to the interior of black holes. Still other solutions describe wormholes that connect different points in time rather than different locations in space, creating theoretical possibilities for closed time-like curves and the paradoxes associated with time travel. The environmental conditions surrounding a wormhole would depend on its location and history. A wormhole formed through natural processes might exist in the vacuum of space, with only the subtle gravitational effects revealing its presence. Alternatively, wormholes created by advanced civilizations might be surrounded by complex structures designed to stabilize their geometry and control access to the passage. The energy requirements for maintaining such structures would be enormous, potentially requiring the manipulation of matter and energy on stellar scales. The electromagnetic properties of wormhole throats present intriguing possibilities for their detection and study. Magnetic field lines threading through the passage could create unique configurations not found anywhere else in nature. Charged particles following these field lines might produce distinctive radiation signatures or create plasma phenomena that could be observed from great distances. The gravitational waves produced by wormhole formation, collision, or collapse would carry distinctive signatures that might be detectable by current or future gravitational wave observatories. These ripples in spacetime would propagate outward at the speed of light, carrying information about the exotic physics occurring at the wormhole throat. The analysis of such signals could provide crucial tests of our understanding of general relativity under extreme conditions. Current research into wormhole physics explores various mechanisms that might allow their formation and stabilization without requiring large amounts of exotic matter. Some theories suggest that quantum effects or modifications to general relativity at very small scales might provide alternative pathways to wormhole creation. Others investigate whether cosmic strings, hypothetical one-dimensional defects in spacetime, might serve as the scaffolding upon which wormhole throats could be constructed. The search for wormholes in our universe continues through both theoretical investigation and observational astronomy. While no confirmed wormhole has been discovered, astronomers examine phenomena such as gamma-ray bursts, fast radio bursts, and gravitational lensing events for signatures that might indicate the presence of these exotic objects. Advanced detection methods might eventually identify the subtle distortions in spacetime that would mark the presence of a wormhole throat. The study of wormholes provides insights into the fundamental nature of spacetime itself, revealing how Einstein's equations permit geometries that challenge our intuitive understanding of distance, connectivity, and causality. Whether or not wormholes exist in nature, their theoretical investigation continues to deepen our appreciation for the remarkable flexibility and strange beauty of the universe's underlying mathematical structure. In contemplating these bridges through spacetime, we encounter some of the most profound questions about the nature of reality and our place within the cosmic architecture that surrounds us, the cold spot in the CMB. Across the entire sky, the cosmic microwave background radiation maintains a remarkably uniform temperature, differing by only tiny fractions of a degree from one region to another. This ancient light, released when the universe first became transparent some 380,000 years after the Big Bang, carries within its subtle variations the imprint of cosmic history. Yet within this gentle tapestry of primordial radiation lies an anomaly so significant that it challenges our understanding of the early universe's structure and evolution. The cold spot, formerly known as the CMB cold spot, spans an area of sky roughly 20 times the apparent diameter of the full moon, making it one of the largest coherent features visible in the cosmic microwave background. Located in the direction of the constellation Eridanus, this region appears approximately 70 microkelvin colder than the average temperature of the surrounding cosmic microwave background, a difference that represents one of the most significant temperature deviations observed in this ancient radiation. To appreciate the significance of this temperature difference, we must understand the expected variations in the cosmic microwave background. The standard model of cosmology predicts that temperature fluctuations should follow specific statistical patterns, with most variations falling within predictable ranges based on the physics of the early universe. The cold spot's size and temperature deficit place it at the extreme edge of what theoretical models consider possible, occurring with a probability so low that its existence suggests either remarkable cosmic coincidence or physics beyond our current understanding. The discovery of the cold spot emerged from increasingly detailed observations of the cosmic microwave background, beginning with early satellite missions and reaching unprecedented precision with the Wilkinson Microwave Anisotropy Probe and later the Planck satellite. These observations revealed that while most of the sky shows the expected small-scale variations in temperature, the cold spot stands out as a coherent region of reduced temperature that extends across angular scales much larger than typical CMB fluctuations. The physical origin of the cold spot remains one of cosmology's most intriguing puzzles. Several competing theories attempt to explain its existence, each with different implications for our understanding of cosmic structure and evolution. One possibility suggests that the cold spot represents a primordial fluctuation, a region where the density of matter and energy in the early universe was lower than average, leading to reduced gravitational redshift of photons traveling through this underdense region. Alternative explanations invoke more exotic physics, including the possibility that the cold spot results from interactions with parallel universes or bubble universes that existed during the inflationary epoch of cosmic expansion. According to these theories, collisions or interactions between our universe and neighboring bubble universes could have left distinctive imprints in the cosmic microwave background, with the cold spot representing evidence of such primordial cosmic encounters. The integrated Sachs-Wolf effect provides another potential explanation for the cold spot's properties. This phenomenon occurs when cosmic microwave background photons travel through regions of changing gravitational potential, gaining or losing energy as they traverse evolving cosmic structures. In regions where matter density is significantly below average, the gravitational potential wells are shallower, causing photons to lose energy and appear cooler when they reach our detectors. Observational studies of the cold spot have revealed additional puzzling characteristics that deepen the mystery of its origin. The region not only shows reduced temperature, but also exhibits unusual statistical properties when analyzed using various mathematical techniques designed to identify non-random patterns in the cosmic microwave background. These analyses suggest that the cold spot may be part of a larger pattern of anomalies that could indicate systematic deviations from the standard cosmological model. The supervoid hypothesis represents one of the most thoroughly investigated explanations for the cold spot. According to this theory, the temperature depression results from cosmic microwave background photons traveling through an enormous cosmic void, a region of space where the density of galaxies and dark matter is significantly below the cosmic average. As photons traverse this underdense region, they experience a net energy loss that manifests as a temperature reduction when observed from Earth. Recent galaxy surveys have indeed identified a large cosmic void in the direction of the cold spot, lending some support to the supervoid hypothesis. This void, spanning hundreds of millions of light years, contains far fewer galaxies than expected for a typical region of space. However, detailed calculations suggest that even such a large void may not be sufficient to explain the full magnitude of the temperature depression observed in the cold spot, indicating that additional factors may contribute to its properties. The texture hypothesis proposes a more exotic origin for the cold spot, involving topological defects in space-time itself. According to certain theories of cosmic inflation, the early universe may have undergone phase transitions that left behind geometric defects in the fabric of space. These cosmic textures could influence the propagation of cosmic microwave background radiation, creating temperature variations that appear as cold or hot spots in our observations. Non-Gaussian features in the cold spot's statistical properties provide additional clues about its possible origins. While most regions of the cosmic microwave background exhibit temperature variations that follow Gaussian probability distributions, consistent with the predictions of inflation theory, the cold spot shows deviations from these expected patterns. These non-Gaussian signatures could indicate that the region formed through processes not accounted for in standard cosmological models. The polarization properties of cosmic microwave background radiation in the cold spot region offer another avenue for understanding its origin. Different physical mechanisms that could create temperature depressions would also produce characteristic patterns in the polarization of the radiation, providing additional observational tests for competing theories. Future observations with improved sensitivity to polarization measurements may help distinguish between various explanations for the cold spot's existence. The implications of the cold spot extend beyond its immediate mystery to broader questions about the nature of cosmic inflation and the statistical properties of the early universe. If the cold spot indeed represents a primordial feature that formed during inflation, its properties could provide insights into the physics operating during this earliest epoch of cosmic expansion. Alternatively, if it results from later evolutionary processes, it could reveal new aspects of how cosmic structures form and evolve over billions of years. The ongoing investigation of the cold spot employs increasingly sophisticated statistical techniques to extract information from cosmic microwave background observations. Machine learning algorithms and advanced data analysis methods help astronomers identify subtle patterns and correlations that might reveal the physical processes responsible for this temperature anomaly. These studies continue to refine our understanding of what constitutes normal variation in the cosmic microwave background, and what might indicate truly anomalous physics. Future observations will play a crucial role in resolving the cold spot mystery. Next-generation cosmic microwave background experiments, with improved angular resolution and sensitivity, will provide more detailed maps of temperature and polarization variations across the sky. These observations, combined with deeper galaxy surveys that can better characterize the matter distribution along the line of sight to the cold spot, may finally determine whether this feature represents exotic physics or an extreme but explicable consequence of known cosmological processes. The cold spot serves as a reminder that even in our well-tested cosmological models, mysteries remain that challenge our understanding of the universe's fundamental properties. Whether it represents a window into exotic physics, evidence of cosmic evolution, processes we don't fully understand, or simply an extremely rare but permitted fluctuation in the primordial universe, the cold spot continues to inspire new theoretical investigations and observational strategies that push the boundaries of cosmological science. I hope you enjoyed this peaceful journey through the cosmos. If you're still awake, feel free to drift further by clicking on the next video right here on the screen. Sleep well, and see you in the next one.